Pipeline parallelism speeds up training of AI models by splitting a massive model across multiple GPUs and processing data like an assembly line, ensuring no single device has to hold the entire model in memory. This course teaches pipeline parallelization from scratch, building a distributed training system step by step. Starting with a simple monolithic MLP, you'll learn to manually partition models, implement distributed communication primitives, and progressively build 3 pipeline schedules.
Did you ever look at DeepSeek's pipeline parallelism algorithm, GPipe, and ever think to yourself, what black magic do these researchers use to conceive of such an algorithm? Well, don't worry, because in this course, we will derive pipeline parallelism from first principles and from scratch so that you can also make such an algorithm afterwards. My name is Kian, and welcome to the Pipeline Parallelism from Scratch course, and let's get into it. And before we get into it, I quickly want to mention the prerequisites of this course, which are both PyTorch and Python. So in order to get the full value of this course, you should have experience with using both of these frameworks. So let's get started. The first step, of course, is going to be cloning the repository, which you can take here or by going to the repo itself, which is linked in the video description, and then just going through the standard GitHub cloning instructions. And then once you've done that, you will find the following menu of files. So let me first bring your attention to the My Work directory, because this is where all of the skeleton code is, which we will complete together throughout the course. As you can see, there are 5 steps. And then moving on, we have docs, which can be ignored because all of the docs are at this website, which is just the same URL, but in the GitHub pages format as the repository. So the index is here, and then you can go through all of the different sections of the homepage, which I will go through one at a time. So there's no need to go at this time and check out the website unless you want to check it out beforehand. And furthermore, we have the source directory, and these are all of the completed ground truth files, which is to say that as we go through the course, every single step here will correspond to one of the files here. So for example, step 1 manual will be the same as the manual file, and this is just the completed version so that it has comments, first of all, to explain all of the steps, like pretty thorough comments, and it also works. So if you have a bug and you can't find the reason why it's not working, then you can simply refer to this. And other than that, there's just the README and main.py, which is also implemented for us. And it's just the runner, which when we go into step 5 and actually implement our pipeline scheduler, it is essentially what orchestrates the entire run. So now that we've gone through the file structure of the repository, let's go through the syllabus. So in this course, we will start with a MLP and train it on a single CPU. It's called Monolith because it only has one device or one GPU, CPU, whatever you want to call it. And the goal here is just to establish a baseline with a sequential neural network that is simply 16 layers. And then we will motivate pipeline parallelism. In fact, we can just discuss it right now. So as you may or may not have heard before, a memory wall is essentially when your model does not fit on the GPU that you have. So there are many ways to overcome this, and one of them is through pipeline parallelism. So in this example, we have a 10 billion parameter LLM, for example, and it has the weight stored in float point 32, which would mean 4 bytes per parameter. And if we multiply 4 by 10 billion, then we get 40 gigabytes. And let's say, for example, we have a 4090 as our hardware. Well, you can see here that the VRAM of this chip is much less than the weights that we have. And of course, you don't simply need 40 gigabytes to run this model. Since you have to store activations, this will require more than 40 gigabytes. So the solution that Pipeline Parallel introduces is model partitioning, which we will discuss in detail. And we will do this first manually. So this is not what you ever want to do in production, but it's just to illustrate the point. And then once we've done this manually without any pipeline, then we will go through the distributed basics, which gives us the foundation for how we will communicate between the different GPUs, because if you didn't know it already, pipeline parallelism requires at least 2 GPUs. It's multiple GPUs which are split up, which are splitting the model amongst themselves. Then we'll talk about the naive solution, and then the 2 sequential upgrades from the naive solution. So the first one is called GPipe, which was made by Google in 2019. And then after that, we have one forward, one backward, which came out in 2021. Of course, the state of the art has improved since then. But if you know these 2, then you already pretty well mastered the concept of pipeline parallelism. So that is our syllabus. And with that being said, let's start off with Monolith. So as you'll see, Monolith only exists in the SRC and not in my work, because we're not going to implement this since it has nothing to do with pipeline parallelism. This is literally just a 16-layer MLP. And since it's only 54 lines, we're going to go through the entire file very quickly just to see what's going on, because this is the same template as all of the succeeding files in the course. So we have a 32 batch size with a hidden dimension of 128 and 16 layers with 50 steps in our training loop. And then we initialize the MLP here. It's called the monolithic MLP. And simply, we take a list of layers. Of course, since it does inherit from the nn.module class, which is the base class for all neural network modules, then we need to call the super method so that all of the parameters of the nn module are initialized. For example, this sets up autograd and also the device tracking, because PyTorch will move your tensors and models automatically from device to device, but this won't be able to happen unless you have the parent method initialized, which is nn module. And yeah, we have our layers here, which we simply append to. So every layer of the model is just a nn linear, which is a fully connected layer with hidden dimension 120 to 120 in this case, followed by a nonlinear activation function, which is just ReLU. So we're really doing the most simple, primitive MLP operations, because this is not the purpose of the course to make some say that our MLP, it's just to have a baseline. And then we have our head, which is what will perform the classification. So I haven't mentioned it, but we're just training an MLP on random data to do binary classification. As you can see, our dimension is reduced from 128 to 2 in the last layer because we want to have 2 classes. And then we take our 16 plus 1 head layers and then use the star to unpack all of those layers into a NN sequential. And then we also establish a cross-entropy loss as our loss function, since it is once again binary classification. Then the forward function is just getting our logits and then using the cross-entropy loss to calculate our loss from those logits. So hopefully up to now, this is all pretty simple. One thing worth noting is that the manual seed is set to 42 in all of our files, so we can have a consistent way of checking results between different methods. And then we'll initialize our model here, initialize the atom optimizer with a learning rate of 0.001. The same thing is done throughout the entire course. And as I mentioned, we are going to overfit to a random tensor of batch size 32 and hidden dimension 128. So the model is literally just learning a random tensor. And then our fixed target is the class of each random tensor. So for every single element in this 32 batch size tensor, we'll give it a class through the torch.randint function, which just creates a tensor from 0 to 1, because the low is inclusive and the high is exclusive, just like range, for example, and it will just be of shape 32. And here's the training loop. We start the training and we'll time it as well. And then for 50 steps, we'll first zero our gradients, so we're not accumulating the gradients unknowingly. And then we calculate the loss. We do the backward pass, backpropagation, our optimizer step, and then every single 5 steps, we will print our loss and the step that we're on, and that's it. So as I said, we're not actually implementing this ourselves. So what we're going to do instead is just use UV run to do this right now. And throughout the entire course, I'll be using UV run, but if you prefer Conda or any other way of managing a Python project, then please do that instead. That's the way I'm doing it in this course. And everything that I do you will be able to reproduce because UV is just really nice and reproducible. So that's my recommendation. Anyways, as you can see in our training setup with 50 iterations, we started with a loss of 0.7 in our cross entropy loss, and then it went all the way down to 0.2436. And because once again we have our manual seed set to 42, this is deterministic. So if I run this one more time, it's the same exact thing. Of course, the time is not deterministic because wherever the memory is happening, like, of course, the memory management that's happening at a very low level in C probably, and the buffer management makes it such that the time is different slightly every single round, but the final loss is not. And if I just show you something here, by commenting out the manual seed, it will just do the default manual seed, and you can see that it's different in terms of the final loss. So the final loss is always changing because I'm not actually sure what the behavior is when you don't set a manual seed. It probably just gives a random seed to the random seed. But in any case, what we'll note here is that the final loss is always the same with our manual seed. So this is our monolith. And now let's come back to our syllabus. So we established the baseline, and it's just an NN sequential with 16 layers. And now, once again, we're going to hypothetically consider the fact that we're just running this on a CPU, of course, and it's a really small model. But let's say that this would no longer fit on the model, and we want to split it in half so we can split it across on 2 GPUs. So we'll be cutting the neural network sequential class into a part 1 and a part 2 by manually passing the output of part 1 into part 2. And this is our first step in my work. So let's open up my work and step 1, which is called manual.py. So here you go. As you can see, it's quite similar in structure to our monolith.py file, except it's got a bunch of to-dos where we need to add the functionality, which will make it sharded across 2 models. So here you can see, first of all, we have part 1, part 2, instead of just the monolithic MLP in the first file. And furthermore, we need to, for example, make our optimizer track both the parameters for the first part of the model and the second part. And then another thing worth noting is that in terms of the total layers, we will not do 4i in range 16 for each model, because then the final model will be double the size as the monolith. So instead, we'll have to divide by the number of devices that we have. In this case, it's 2. So we'll do 16 divided by 2. And every single part, or the 2 parts, will hold 8. To be more precise, this one will hold 8, and part 2 will hold 9, because it's also storing the classification head. So that's the context that I'll give you. I would highly encourage you to implement this, or try to. Once again, all of the solution is here in manual.py. So if during this implementation you get stuck somewhere, you can refer to this. And I will not be mentioning this in the future, which is to say, now we're just going to start implementing this. And when I do step 2, I'm not going to say, okay, go try it on your own with comms.py. But I would recommend to do this through the entire course if you would like to, because that's more active in terms of learning as opposed to passive. But now that I've said that, we're actually going to implement this together. So let's start off with part 1. And once we've done this, we can copy paste most of what we've written here in the part 2. So as you remember previously, we have to initialize a list called layers, which stores all of the nn.linear fully connected layers. And then we will just iterate over the total layers here, which should come up here. And then divide this by 2 using integer division, because one thing worth noting is that if you divide by 2 like this, if I just open up a Python terminal and do 16 divided by 2, which is what we're going to do in the code, it gives you a float. And I'm not sure if this will cause an error with range, if it will automatically input it as an int or not. But just to play it safe, we want to do 16 divided by 2 integer division. And one thing worth noting is that we're never going to have an odd number of layers since we can choose that. But if we actually do have odd number of layers, then this will prevent an error where you do 4i in range like 7.5, which will definitely give you an error. So now that we've done that, we're going to initialize our part 1 with the layer, the nn layers, as we already mentioned. So we have to append them, nn linear, and the dim is going from dim to dim. So pretty simple. And then we also want to add a nn .relu, which does not take any parameters. So I can just delete this. And this is everything that we need in terms of the layers for our NN sequential. So we'll say self.net equals nn.sequential of the unpacked layers. So once again, the star iterator or the star operator just takes a list and then unpacks it, which is what sequential expects as its argument, if I'm not mistaken. So if we come here, yeah, it's an order dict. I don't know how the exact input requirement is, but what I do know is that this is the way that you should input it in order to get a proper neural network. And then our forward method is already implemented because it's kind of simple. We didn't really need to do that on our own, but all we do here is return self.net of x, and we don't return the loss. So one thing worth noting here that's already different is that the forward for part 1 and part 2 are not the same, because this is just an intermediate step, right? This is the output of the 8th layer, whereas here it's the output of the entire neural network, at which point we calculate the loss. You can calculate the loss at step 8, but then it defeats the purpose of having 16 layers. So now what you can think here is that this activation, which is called the output of this part 1 neural network, will be fed into part 2. And now we need to implement part 2. But as I mentioned earlier, we can copy most of it and then just add the LLM head. Not the LLM head, but the neural network head, because it actually needs to perform the classification. So before we initialize our self.net, I'm just going to do self. What am I going to do? I'm going to do not self, but rather layers dot append of. We're going to append a nn dot linear, and this nn dot linear is going to go from dimension dim to dimension 2 because we're doing binary classification. And then, yeah, we should be fine to create our net, which is saved as a member of the part 2 class. And then in our forward method, we simply do the same step as here, which is self.net of x, which calls the forward method on the sequential neural network, which will just do a forward pass. And of course, as you know, we don't need to implement backward in PyTorch because it will just take the forward computational graph and do this in the opposite direction with AutoGrad, which will maintain all of the gradients and all of that good stuff that we don't have to worry about anyways. And then once we have this, these logits, which is the output of our classification head, it will be 2 logits, one for class 0 and one for class 1. And since we do input a random tensor, these logits don't really have any meaning whatsoever. But of course, if you want to interpret this in like the image classification sense, maybe our data set is dogs and cats, and we want to classify between these two. So that could be a potential example, but for simplicity's sake, once again, we're just learning a random tensor, and then we calculate loss. Oh, and that's the one thing that I forgot. We didn't actually initialize our loss function. So it's great to notice that now and not later. So this will just be nn cross entropy loss. The criterion computes the cross entropy loss between input logits and target. So we once again have the targets here, but not the targets here. And this is because we're not calculating the loss in part 1. But even so, the targets are just fake values. But if we take the dog cat example, once again, for every single input data, we would have the ground truth because it's supervised learning, so that the model can learn which images are cats and which images are dogs. And I'm just going to check here. I don't think this takes any arguments. Let's just look at an example. I would really recommend to look at the type hints that pop up in your IDE for PyTorch. It's really, really helpful. So once again, here you can see that it is not initialized with any arguments. And we also can call this self.criterion. That's a really common name used. Here it looks like they call it loss, but they use the word criterion. So criterion and loss in this case are interchangeable. And now, unless I'm forgetting something, everything is set up such that when we do the forward pass through these two networks, we will call self.loss on the logits, which come here from the neural network, and we will compare this to the targets to give our loss, and then in the backward pass update our weights with the gradients. Okay, so we did that. Now let's go to the next to do. In this case here, I didn't actually say what we need to do. So in essence, we are checking if CUDA is available. So what I didn't mention is that in this course, we are going to assume and just use the CPU and just shard over virtual cores as opposed to using the GPU, because I don't have actually access to a GPU, and I'm assuming that most of you don't. And moreover, to do pipeline parallelism, you need multiple GPUs. So for sake of simplicity, we're going to be using CPU as the default torch device, but the repository still has support for GPU. So if you have, in this case, 2 GPUs, then we're going to implement the proper device handling to allow the model to move the tensors and the different neural networks onto the correct device. So first of all, we check if torch.CUDA is available. So if you come into your own terminal with UV run Python, I'll show you how to check this for yourself. So first thing is I'm going to import torch, and you might be wondering, how is it possible that it's not giving an error? And I'll just show you just so we can check for ourselves. If I just run Python 3 outside of UV and try to import torch, we'll get an error because I don't have it in the virtual environment. But since we do have torch as a dependency of our project, and furthermore, I have opened the Python interpreter with UV, then everything's handled for us. So this course is almost becoming a UV advertisement, but it really is amazing to use. So what I was going to do is, I think we copied it. Oh, okay, I didn't copy it. I thought I copied the value. So let's come ahead here and copy if torch.CUDA is available. Geez, man. And then we'll see that it's false. Because I don't have a CUDA device on my computer. But if you do, then you would get this value here. And furthermore, you can see the number of devices available by calling the device count. Oh, it's because I just found a bug in my code. That's amazing. We just called the function. We just initialized the function, but we didn't actually call it. So you can see here that we have 0 in terms of the device count. So this is both checking, is the device available, and are there more than 2? Or more than or equal to 2, because in this case, we need at least 2 GPUs. And then if that is the case, then we set CUDA to true. So now here we can say that if CUDA, we will do something. And then if not CUDA, we will do something else, because we want to move our model, which in this case is part 1 and part 2, onto CUDA if we do have those devices available. So in the case that we don't do anything, because if you didn't know this, in PyTorch, the tensors and models that you initialize are always initialized on the CPU by default. You don't have to specify 2 device CPU, but if you want it to be on your GPU, then you do. So what we're going to do here is initialize our neural network, right? Part 1 is initializing a 8-layer neural network. And then we're going to do to torch.CUDA.device. And this will select the relevant GPU. In this case, we'll just select GPU 0 because this is the first layer, and then GPU 1 because this is the second layer. Of course, it doesn't really matter. You could flip the order of the GPUs you put the model on. It's just a number for the index, but let's be consistent here. So now, if we have GPUs, we're going to put the model 1 on the GPU 0 and model 2 on GPU 1. And once again, the reason for this is, let's say in a hypothetical case, we don't have enough space to store this model on 1 GPU. We're going to do that. Okay? And we're going to do the same for all our input tensors, because the tensors that you input in PyTorch need to be on the same device as the model itself. If you think about it, if you have your model on a GPU and all of your data on the CPU, then you'll have to route all the data to the GPU, do the calculation, then route it back. This will be incredibly inefficient, and it might even give you an error. I'm not sure how PyTorch handles this if you give it a mismatched input model pair, but to avoid anything happening in terms of mismatch, we're just going to do it properly to begin with. So let's say, once again, if CUDA, we're going to just duplicate this because we need it twice. tab, and then if not CUDA, then we do nothing once again. So we don't need to do anything. So let's look. The input needs to go to device 0 because it starts on device 0. In the forward pass, it goes to the first layer of the first GPU. And then the target, though, if you remember, is only ever seen by part 2, right? Targets is here, and then part 1 never has it because it doesn't calculate the loss. So it actually goes straight to the second GPU. And this is done here. Now let's go to the next to-do in our training loop. All right, here it says device switch. What does it mean by device switch? What it means is that if we are using a GPU, then once we get our activations from part 1, which is the output of the forward, so return self.netx, then we need to move this to the second GPU if we are using GPUs. So let's do that right now. If CUDA, we'll do hidden dot to, I think we have it in our clipboard, and then we'll change it to torch.cuda.device1. Okay, now that this is done, and then we'll also do something called retain grad. So I'm just going to show you guys right now what I mean. I'm going to do hidden.retain_grad. And what is this doing? So here you can see I have a print statement which prints the requires grad element of hidden, the grad itself, if whether or not it's none, and then the grad itself. So what we need to know is that in PyTorch, there are certain tensors which have requires grad equals true and certain that don't. As a general rule, any neural network parameter has requires grad equals to true because you want to store the gradient such that you can update all of the weights during the backward pass. And to that end, hidden actually will also have requires grad equals true. So I just realized we've done the implementation. So let me first run this once and then I'll explain what hidden retain grad does. So let's get out of the Torch interpreter and we will run my work. And if we get a bug, that will be cool because we can debug it in real time, but I don't know, I'm kind of confident. So let's see what happens. Oh, okay. This is amazing because I kind of left this bug as a booby trap because if we look at manual.py in our solution, what do we have? Oh, actually, no, let's not look at the solution yet because I don't want to spoil it. If we look at the monolith, we have optimizer equals optimal atom model.parameters, and that's it. So first of all, we know that we are missing something because we don't actually select the parameters, but also there's something else. So first of all, let's just add the parameters because currently we're just giving it the NN sequential itself and the optimizer doesn't know what to do with it. So where are we actually initializing our optimizer? Right here. So let's do dot parameters and we need to call this. And then we also need to convert these into lists, both of them, because we're adding them and yeah, you can't, actually I would like to see what the error is because I didn't ever check this for myself, but you can't add parameters because they're generators, you can't add them to each other. But now, if we convert these generators into lists, which will just iterate over the entire generator and then give us all of the output parameters of each of these two neural networks, then it should work. Unless we do another thing wrong. Okay, I have a comma here. Why do we have a comma here? I don't actually know why. It's because the comma should be there. Okay. Let's see. All right, so it works now. And so the optimizer is fine now. This is the kind of trap that's in the code. So we can first of all see something really cool, which is the fact that the final loss here is the same as the loss for Monolith. So let's look, if you forgot, it's the same. And in terms of the time, we can run it once more to see how long it takes. I wouldn't really put too much weight into the timing here because once again, you can see here, it was actually 0.1 seconds faster than the first run. And my guess is that it's cached some values in my Mac and makes it go slightly faster the second time. But in any case, what's worth noting is that since we do have the manual seed set up to 42, then everything is great in terms of the reproducibility. But more important than that, let's come back to these print statements. So let's see what happened here. We had let's first try it with retain grad equals false, because you don't even know what this means yet. So we'll just see what the output is without anything colluding it. So first of all, we have print hidden.requires grad, which is true. And the reason why this is true is because when we have a output of a neural network module, in the computational graph, the output of a calculation, which is itself created by parameters which require grad, will also require grad. This is just how the require grad inherits from its children, essentially, in PyTorch. So this will always be true for hidden. We don't have to worry about that. And what this means is that when we do loss.backward, we don't have to worry about the gradients not flowing from part 2 to part 1. And now I'm going to check something, which I don't actually know if it'll work, but I'm still going to try it. And what I'm going to try is to say hidden.requires grad equals false and see what happens. I haven't tried this myself, but it just came into my mind. In theory, this should break the connection between part 1 and part 2, because now we will no longer be storing the gradients between the two. But let's see what actually happens in the code. Okay, let's see what it says. Runtime error. You can only change required grad flags of leaf variables. If you want to use a compute variable in subgraph that doesn't require differentiators, use var no grad equals var.detach. Okay. I see. Okay. Essentially, it's telling us that we should detach hidden, which will remove it from the computational graph. And let's see what happens now. I think it will give us an error. Okay. So the error we actually got is incorrect because I forgot to change hidden equals hidden.detach instead of saying hidden requires grad, because we want to change the entire tensor. And here, okay, we can see that exactly as we prophesized, the training loop is messed up. What I'm trying to say here is that the loss is not propagating backwards from our model in part 2 to part 1. And this is because we detach the model here. And now if I print hidden.requires grad, what happened? Hidden.requires grad, we'll see that it should be false. And this means that when we actually do backpropagation, there's no learning happening in part 1. So let's just run this once and see what it says. The Boolean object is not callable. That is true. It's not callable. Okay, it's still not callable. Did it not update my code? Print hidden.requires underscore grad. Okay, boom. Yeah, I printed it way too many times, but you can see that's false. And at this point, what this means is that somewhere in the computational graph, PyTorch is kind of just fumbling around, doesn't really know what to do, because we detach. And when we detach a tensor, it loses its gradients and sets requires grad equals to false, as you see here. So this was just a mini experiment, which is really cool. Now let's get back to the subject of step 1, which was, if we remind ourselves, to calculate with part 1 and part 2 and get back this final loss. But even though requires grad equals true in this case, what we notice is that we have our gradient equal to none, which means it's false. And also we have no hidden grad. And this is because after the backward pass, PyTorch no longer needs the gradients of intermediate activations, which hidden is in this case. So it will empty them to save memory, which is really good. But what we need to know is that when we actually do pipeline parallelism here, we will be moving with a communication primitive, which is just called dist.send and dist.receive in the message passing interface, which is just the PyTorch way of communicating between different models and devices. In this case, we will need to send our hidden activations between the two models, because the activations are used in order to calculate the partial derivative of the loss with respect to those activations, aka inputs, so that we can propagate the back so that we can propagate the locks backwards through the graph. And even though we don't need to set retain grad to true for this network to learn, it will just print what the model is actually sending backwards. So let's come here, and now we can see that once we say retain gradients true, it actually retains it in the hidden.grad element of our tensor, and it is just here. So first of all, you can see hidden grad is not none, so it's true. And in this tensor are the gradients of hidden, which in the pipeline parallelism that we'll be implementing very soon will be sent backwards from part 2 to part 1. And if you want to know what's sent forwards from part 2 to part 1, then we can just print hidden itself. So we can see that this is the vector that is sent in the forward pass. It's the actual activations of hidden, just this, because we can see that when we input our hidden vector into part 2, these are the activations themselves, the input to the second model. And then the gradient, which is in the backwards direction, is something else, because the gradients are the same dimension as our hidden input activations, but they are instead telling the model how to change the weights of our model in order to decrease the loss. And one last thing that I'm going to do is calculate the shape, just to show you guys that the gradients and the model itself have the same shape. So let's look at this real quick together. 32,128, 32,128. So there you go. We have now implemented the step 1 manual, which all it does is make on a CPU 2 fake models and splits them up in the middle, and then does the exact same loop, as manual.py, which is right here. And if you actually have a CUDA GPU, then you can do this for real with all of the device management, which is really cool. So if you do, then please let us know how that goes in the comment section. And now we can move on to step 2. So now that we've done the manual, we can see that even on one machine, you still have to manage the handoff of the activation and the gradients. And just to highlight where that happens, the handoff of the activations happens here. And then in fact, the handoff of the gradients is done by backward. So we don't really have to handle that. So I should probably modify the outline to rectify that error. And now that we've done that, let's talk about distributed basics. So in this stage of the course, we're not so much going to be implementing pipeline parallelism as implementing the communication primitives, which are in this case the send tensor and the receive tensor functions, so that we can actually communicate between our different GPUs and send the weights between them. Okay, so the distributed basics comprises 3 things: rank, world size, and process group. Let's go from bottom to top. The rank is just the ID of your GPU. So if we have 4 GPUs, we have ID 0, 1, 2, 3. That's simple. The world size is the number of GPUs. Very simple as well. But then there's also the process group, which is used in PyTorch in order to establish the group which inside of which we will have our communication. So this may or may not make sense as of right now, but once we implement it, then it will be much clearer. So let's come and open up our step 2 comps and get into the implementation. So let's look at the functions that we have. First of all, we have an init distributed, which initializes the distributed process group. Once again, this is the stage where we have to call init underscore process group and initialize the communication, or the conference call if you'd like to say it that way. And then if we come back to step 2 comps, we reach the state directly from the environment variables set by torch run as well. And this is already done for us because it's not really interesting to implement this on your own. So what is torch run, first of all? If I just come here and say uv run torch run, we'll obviously get an error because we haven't given any arguments, but torch run is how you execute distributed code in PyTorch, which is to say, as soon as you have more than one GPU, you can no longer run a single file, main.py, across all of your GPUs. You actually need to run one process of each file for each device. So what torch run does in essence is it creates a copy of your script for every single GPU and then runs it on that GPU. Okay? And this is why it actually gives us a local rank. So when you think of step 2 comms, which is going to give us our communication, what you should really think of is 4 copies of this file for the 4 GPUs, if we're going to use this example, which we are. And for this reason, we'll get local rank from 0 to 3 inside of this init distributed method. And furthermore, we get our world size and our rank. And as the comment says here, once again, it's set by torch run. So these environment variables are initialized by torch run itself. We don't have to worry about that. But now this is done, we still have work to do, which is to say, set up our device. If we're using a GPU, then we need to set our device to CUDA. If not, then it should be CPU. So the best way to do this is device equals CUDA if torch.CUDA underscore is available, or I think we just do dot is unavailable. There you go. And then it will be CPU otherwise. So one thing that I didn't mention is that we should specify the device itself, and we have local rank. So very conveniently, we can just specify local rank here. And we also need to add a colon. So in essence, when you have a device and multiple GPUs in PyTorch, you just specify which device it is by CUDA, comma 0 for the 0 GPU, CUDA colon 1 for the 1 GPU. So we're just gonna do this. And in this code, we're just gonna assume that you have 4 GPUs. We can also add a condition if the device count is less than or equal to 4. If it's less than 4, actually, then return an error. But let's just keep the code simple for now. And then we'll initialize the group. So once again, it's going to be dist.init process group. So let's look at the method description here and see what it says. Okay, this doesn't seem too easy to read. I don't know where the there you go, it went. So it initialized the default distributed process group. This will also initialize the distributed package. There are 2 main ways to initialize the process group, etc., etc. We already know how to do this. In essence, okay, it doesn't have any examples, but in essence, this is what's going to establish our communication. You can think of it as the conference call between our different GPUs. So the backend will depend on the type of devices that we're using. So here we actually need to check again if we have our device, if we have GPUs available, and then if not, we're going to do something else. So here and then else, and we're going to do a different type of distributed init process group call. So if we have GPUs, which is the case here, then we're going to use the NCCL backend, which stands for the NVIDIA Collective Communications Library. And this is just how GPUs communicate with each other. And then the second argument is what? The init method, which we're not going to use. We're going to use the first way, which is to specify store, rank, and world size. And store here is the type of communication backend that we're using. So we just input rank and world size here, as we already got them from torch.run, and then world size. Boom. And then I'm just going to copy paste this here, except we're going to use glue. So if we look back at the different types of communication backends that are supported, we have MPI, glue, NCCL, UCC, XCCL. Notably, you'll see that MPS is not supported, so Metal Performance Shaders, which is used in Silicon Macs. So even me using my Mac, I was unable to try this on the GPU because we don't actually support distributed communication yet in PyTorch on MPS. So in this case, even if you have a Mac Silicon chip, you still have to use a CPU with glue, which is the communication platform that we have to establish here. Okay, so now this is actually everything we need to do in order to initialize this distributed process group. So let's give ourselves a pat on the back, and we just return rank, world, and size. Rank, world size, and device for later reference. And then now in pipeline comms, we have a few things that we need to check. So first of all, we have our init method, and we want to come ahead and save our rank as well as our world size, because this is what you do in an init method in a few words. And then, okay, that's weird how it did world twice. Anyways, there you go. And then what we're going to do with these values is say whether or not we are the last or the first GPU, because it's very important. Why is this important? For example, the first GPU does not send any gradients to a previous GPU because there is no GPU before it, and the last GPU does not send any activations to another GPU because there's nothing after it. So we'll just say self.last, I forget what we said in the official library, but it doesn't really matter, equals self, it doesn't equal self. So if we want to check if the GPU is the last one, we'll just do self.worldSize, and then we will take self.rank, and we'll say, is this the same as self.worldSize minus 1? So if we have 4 GPUs and the rank is 3, then 3 equals 4 minus 1, and this is when we want self.last to be true. And I did say that we don't want to look at the comms.py sheet, but I really want to quickly check what we called it. We called it previous rank. Okay, no, we didn't call it that. Okay, we did call it that. So I just realized we don't want to use self.last just yet. From seeing that, we're instead going to call them something else, and then this will be much more useful. So self.previousrank is going to be the value of self.rank minus 1 if self.rank not equals 0, else none. So this is how we're going to check if, for example, you're the first GPU. If the previous rank is none, that means that there's nothing before you. And then now we can check with this condition here. So sorry for that mix-up, but it will just be self.worldSize minus 1 or self.rank or self.rank plus 1 if the following condition is true. If we have this self.worldSize, shoot, sorry for this blooper, guys. I really need to copy this instead. So there you go. And since I confused you guys slightly, let's just go over what we just did. So the previous rank, we need to call this next rank. The previous rank is equal to self.rank minus 1, which makes sense. If you rank 1, then your previous rank is 0. If you're not the first GPU, otherwise it's none. Here, the next rank is the self.rank plus 1. If you're not the last GPU, so we need to change this to not, else it's none. Okay, so this is all set up really well. Now we will come and implement these 4 primitives. What are the 4 primitives? First one is send forward, send activation to the next GPU. Next one is receive activations from the previous GPU. After that, we have send gradients back to the previous GPU and receive gradients from the next GPU. So what you notice here is that every single function has a receive and a send, because if you send something to somebody, then you also need to have the corresponding receive function. And for send forward and send backward, it's really simple. We just come here and do dist send, and it will send a tensor synchronously. And all we need to specify is the tensor itself that we want to send, which is an argument of our function, so we don't even need to specify it. But more importantly, we need to specify the destination. So that is simply the ID of the GPU that we want to send it to. And let's just come here, input our tensor, and then input self.nextRank, since we're sending, to the next GPU. And one thing that I'll say right now is that, of course, if you called this on the last GPU, you'll get an error, but we're going to add the conditional statement, not here, but in the function that calls it. It will just make the logic slightly simpler. So, and it will also make the code more readable. So we're just going to do that. With that being said, we have finished our first function, so that's great. Receiving is slightly more complicated. You'll see that we have not only a shape device, but also a dtype. So 3 parameters. And this is because we need to specify the tensor which we are going to receive the data onto. If you've ever used malloc in C, this is kind of like a really tuned down version of what we have to do with malloc, which is to say, like, specify a block in memory. So we'll return a tensor, first of all, because when we receive a tensor from receive forward, we want to actually return it back to the function that called it so they can actually get the tensor. When we send something, we don't need to return anything because we're just sending it a value. But when we receive something, we need to return that value that we received. So what we do here is tensor equals torch dot zeros. So we just want to initialize a vector of zeros. You could do also torch.ones or torch.rand. It actually does not matter. And then we will put the shape, the device, and the data type. Okay, and though this will mean that the tensor will be mapped onto the proper device. If we're using a GPU, it'll be mapped on the GPU, and then it will also receive the correct data type. But so far, all we did was return a tensor of zeros. So now we need to do dist dot receive. And what are the arguments to this function? We have the tensor that we just made. So tensor, and then the source. So where's the source? Since we're receiving forward, we have to receive from the person that's previous to us. So self dot previous rank. All right. So now we have two functions down. Let's go down to send backward. This one will send gradients back to the previous GPU. So we need to send to the previous rank. And in fact, this function is almost identical, except we will change next rank to prev rank. So you can see that these functions are, kind of mirrors of each other. And we can also just copy paste this to receive gradients from the next GPU. So if I'm not mistaken, what we need to change here is just previous rank to next rank. And we'll go over it once to make sure that we are doing it properly. So what's happening here is that in receive backwards, we're receiving gains from the next GPU. We initialize our tensor to zeros, receive it from the next GPU, and then we return that tensor. So just like that, we've actually already implemented comms. So you should be proud of yourself because we're already 2 steps into our course. And one thing that I wanted to note is that if you look at the type hint of these distributed protocols or primitives, you say it says receive the tensor synchronously, both for dist.receive and sends a tensor synchronously. So when it says this, of course, you think that there's an asynchronous method, which there is. And this is what's used in production because when you have asynchronous processes, then you can essentially overlap computation with communication more effectively, but it also introduces much more complexity. So for the purposes of this course, we're only going to use synchronous operations, And what this means is that when we call receive backward, as soon as we reach this method, the code will not go anywhere until it actually gets the tensor that it is supposed to receive. So what you can imagine is that if we're running with 2 GPUs and we're waiting for GPU 1, so the first GPU, to do a computation, and then we need to receive the forward from GPU 1, we're going to be waiting here the entire time at dist.receive in the second GPU until the first GPU sends it. And once again, I want to emphasize that here, I don't know why we have this in the top. Here, we have 2 copies of this file. One copy with local rank 0 and one copy with local rank 1 because torch run makes a copy of each script for distributed training or inference, whatever you want to do. So just to be extremely clear on this point, as soon as we run something with torch run, let's say 2 process nodes, which is 2 devices, that could be 2 GPUs, any script that is implemented as its argument, such as these comms, will be run in 2 separate instances, once for the first device and another for the second device, with local rank 0 for device the first one and local rank 1 for the second device. And when we come down here, let's say that we're running the part 1 and the part 2 sharded MLP. In the entire first part, the second GPU is simply stuck at this receive forward function because it's waiting to get the activations from the first GPU so that it can compute its own activations on its part of the model, which means that until the first model computes the GPU and calls send forward to do this dist send to next rank, which in this case will be 1 because we have 0, then the next rank will be 1. This entire time, the GPU 1 is just waiting here to receive the tensor from the previous rank. So nothing's happening. It's just waiting because it's synchronous. As soon as it does receive that value from the first GPU, then it will complete this function and then return the tensor and then start its own activation forward pass. So you can do the exact same logic or reasoning here for the backward set of distributed communication primitives, but in that case, it's the reverse order. It's that the first GPU has to wait for the second GPU to give it its gradients. So there you go. I once again want to emphasize this because it's not easy to think about distributed code because you have to picture two instances of any script. If you have two processes, or if you have even more, you have to picture 4 happening simultaneously. So I hope this makes sense. So now that we have comms done, let's go back to our syllabus and see what's next. So we're still in distributed basics, but now we have a lab, which is to spawn 2 processes on GPU or CPU and ping pong a tensor. And this is the command that we're going to use to run that. So let's come and open our step 3, which is called ping pong. Okay, so you can see it's pretty bare bones. So we unfortunately have to do a lot of implementation here, but let me give you an introduction to what we need to do. And it's pretty well documented here in the doc string. It says, send a tensor from device rank 0 to device rank 1 and print to verify that you actually sent it. So we can see that I already have the conference call establishment, which is just init underscore distributed, which will set up the collective communication between these 2 devices. And this will return rank, world size, and the device that we're on, just as we set it up, if you recall here, which is important. And then we're going to use this to decide which device that we're on and output the corresponding value. But before we do that, let's just see what happens if I print these values. So print rank, world size, and device. And we're once again going to use torch run here. So torch run, UV run, torch run, because we didn't activate the virtual environment. Torch run on its own doesn't work. But if I do UV run torch run with the following parameters, so you can see here, we have n pros per node. And all this means is that how many GPUs do you have? Or CPU processes. So we have 2 in this case. And then we need to specify the file that we want to run. You can see here that this is the training script. So I'm going to come into my work, and step 3 is what we're going to run. So just to verify here, we have 2 GPUs or 2 virtual GPUs. In our case, we have CPUs. And you might be wondering what's nodes? That's the number of computers that you have, or number of clusters. So maybe you have 2 clusters of 2 GPUs. In that case, you would do number of nodes 2 and number of processes per node 2, which gives you 4 GPUs in total. But we don't have that in this case. So we're just going to run torch run. And it looks like, I realized that we don't have this working because we're in a different directory. So instead, I need to say step2.com. So this is good because we will change this for the course. So by the time that you read this, it would actually be step 3 underscore comms. Sorry, step 2 underscore comms. I can't read. And now it should work. Let's see what happens. Okay, guys, we got a bug. That's cool because now we can debug it together. So what went wrong? Oh, okay. No, that's not the error. What actually is there? Let's look at the error, guys, together. As you can see, torch run error logs are not the simplest to read. Okay, so we have a bug. For some reason, it's trying to initialize a process with nickel, even though we have a CPU. So why is that happening? Let's come and see, because I think I have the logic reversed then. Device equals CUDA if torch dot is available. And then this, we will init the process group with nickel if torch.CUDA is available, else dist with glue and rank world size. Actually, this does look correct. Let me just, of course. The fact is that with this type of conditional statement, it will still call this, if I'm not mistaken. So I think we need to just make this a strict conditional statement, and this may fix the bug. If it doesn't, then we'll try something else, but let's see what happens now. No, okay, that was not there. I think then I've misread what's happening here. Okay, no, it is better now. We have glue, and then what else is happening? Right, I can see now our error was quite obvious. It's that we didn't wrap these strings around the torch device call. So literally our device was the CUDA string, and it wasn't the CUDA torch.device of the CPU. So now if I fix this, it should work. Let's try one last time. Okay, now I finally realized the other error is that we need to use keyword arguments to establish these values of rank and world size, because they're not the actual second and third arguments in the code. So we'll say rank equals rank, and then world underscore size equals world size. Okay, now I promise this will work. Please work. There you go. Okay, so we have a working version of the code, but now we need to actually implement the ping pong itself. But what I wanted to point out is that we now get a strange input, which is to say the two values are printing one on top of the next. So if you look here, we'll have rank, in this case is 1 for GPU number 2, and then the world size is 2, and the device is CPU, and then for world size with rank 0, it's 0 to CPU. So you might be wondering, why aren't these printed nicely and they're kind of interleaved? It's because, well, if we try this one more time, we might get it happening. So you can see even here that we have, oh no, this time we get the same result, right? You can see now we have slightly different result. It's because when you have this distributed framework, with the way that the memory and the buffers are loading this information, it's not actually deterministic. So finally I got it. This time we actually first printed 0, 2, and CPU, which is for device 0 of rank 0, and then 1 to CPU, which is for device of rank 1. And this is just to show you that when you do this, sometimes the print statements are working in a strange or asynchronous way. And this is because we're running distributed code. And lastly, I want to once again highlight the fact that we are running 2 copies of this file. So we have 1 copy running on device 0 and 1 copy running on device 1. And for this reason, we get 2 print statements, even though there's only 1 print statement here. And I've never tried this myself, but if we run just the file on its own, we'll probably get an error, because we need to use torch1 when we're running distributed code. But let's just see what happens to make sure that it does give us an error. All right, yeah. It doesn't know where the rank is because, right, if we come here in comms.py, the rank is initialized by torch1. Okay, so now we have this done. Let's actually check what device that we're on. So if device equals 0, we'll do something. And then, I don't want to do it 3 times. If device equals 1, then we don't want to do something else. So in this case, the function says send a tensor from device rank 0 to device rank 1 and print to verify. Okay, so what we need to do first of all is a tensor creation, right? We want to actually make the tensor. So we'll just do tensor equals torch.rand of 3. And what does that give us? Actually, we'll just see very soon. It'll just be a random tensor of 3 values. And then we're going to say tensor. So one thing I forgot to do is actually initialize our communication class, which is pipeline comms. Without doing this, then we won't be able to actually perform the communication. This is the class which gives us our primitives. So we need to give it the rank and the world size. Boom. And then now we're going to do communication dot send forward. And then we're going to send a tensor. And since this does not return anything, then we don't need to return anything because that's not what we do when we're sending. We don't want to capture any values. We only do it when we're receiving. And we'll say print sent tensor. So this will only once again work if local rank is equal to 0. Ooh, okay. I just realized I put device instead of rank. So this should be rank. And then now we will do, first of all, communication dot receive forward of the tensor, but we need to know its shape. So the problem here is that when we run this code on the device of local rank 1, it will not know what the shape is since we have initialized it in the rank equals 0. So let's just take this out of the, oh no, we don't want to take it out of the if, because the whole point is that we only want it to exist on the device 0 and then set it to device 1. So instead, we're just going to assume that we know the shape, which is set to 3. So what are once again the arguments here? I forgot. The shape, which is 3, and then the device, which is device. And we already have that as a parameter of the return to init underscore distributed, and then dtype is optional. So now we can say print received tensor, and then the tensor. And now if we run this, it should actually work, which is amazing. What did we do? I think we still have something that I wanted. Yeah, we're not actually using torch run. Of course, guys, we need to use torch run when we want to run distributed code. Okay, I keep on saying we're not gonna get errors, but we do end up getting an error. And it's because we never actually, okay, first of all, we never actually captured the tensor. And I think that's there. Yeah, it is. Okay. So first of all, you can see we set the tensor of this, and then we received it here. And this is only possible because we have implemented the send forward and receive forward. Otherwise, it wouldn't work. And we can actually just change these to backward because we're not actually doing any backward passes right now. It should be the same. Let's see. Yeah, it should be the same, except the one problem is that the direction will be flipped. So if we do send backward, then we'll have to change the device check. So let's change this to backward. I'll show you, we should get an error here because this should be rank 1 and rank 0, right? But if we change this to rank 1 and this to rank 0, then now we're sending it backward. So it actually works. And this is really amazing to see. We received the tensor of this and we sent the tensor of this. So this is the ping pong example, which establishes the communication which we need to use when we actually have our pipeline parallelism, splitting up the models and sending the data between them. Something I really want to quickly introduce before we move on to the next point, though, is something called torch.distributed.barrier. And what this does is it forces, as we can see here, the processes to wait until the entire group enters this function. So this is mostly useful for asynchronous code where you have many processes happening in different speeds and you want them to all reach a certain point before they move on to the next one. So this isn't extremely useful for synchronous code, but it's still interesting to implement it and see what the effect is. So the first thing that I want to try with this is to put it within one of the conditional statements of the different device ranks and see what happens. So if we just go uv run torch run, I think this is what we want. And what this will do is it will cause the code to not terminate. And why is this the case? It's because once again, as we read, it says it waits until the whole group enters the function, which in this case is these two GPUs or these two devices. In our case, it's two CPU cores because while we're not splitting on GPUs, we're splitting on the cores of our CPU. But if I now come, you can see that this code will never actually terminate because it's waiting forever for the first core of our CPU to enter this barrier, but it's actually not going to get it because it's only happening if you're on rank 1. Now, if we duplicate this and put it down here, we'll see that the code will run as expected. So let's terminate this process and go through it. Boom. So as soon as the two devices reach this barrier, then they will continue on. So this is really good once again for synchronizing asynchronous code, but since our code is already synchronous, it doesn't really make a difference. And one last thing I'll show you is that if we put this before the conditional statements, then both of them will see it at that point, and the code will also run properly. So if you're ever looking into implementing these primitives in an asynchronous way, then this is a cool method that Torch implements, which allows you to temporarily make your code synchronous. So there you go. Now we have done step 3. So we're 60% through the steps in this course. I will note though that the step 5 is the longest, so let's not get too happy. But now that we've done this, we are going to first create the model, which will be sharded along the amount of devices that we have. So in this class, which is step 4 underscore model.py, this is once again mirrored here. So you saw it's only 35 lines. This is going to be really simple to implement and really quick, except the input parameters here are slightly different. As opposed to the step 1, where we had the part 1 and part 2, you can see here the init method only has dim and depth, but in here the init method has hidden dim, total layers, rank, and row size, because we need to know which GPU we're on in order to determine how many layers that we need to make. Okay, so first of all, calculate how many layers this GPU is responsible for, and this is pretty easy. We'll say the number of layers is equal to the total layers divided by the world size. So the number of GPUs that we have divided by, so the number of layers that we have divided by GPUs. So if we have 16 layers and 4 GPUs, then it's 4 layers per GPU. Let's just call this number of layers. And then what we want to do is build the stack of local layers. So this is going to look really similar to what we did earlier. So because of that, I'm just going to come into my copy paste history and paste it here. Of course, we'll have to change a few things. So we'll say for I in range, number of layers, because we've already calculated it. So even before we actually did the division. And one thing I just realized is that we should make this integer division instead of float division. We will take the dim. So here, for some reason, we have it set to hidden dim, but we'll just change that to dim. The total layers, okay. So this is all set up. But one thing that we need to know and don't forget is the fact that in this case, when we had part 1 and part 2, we had 2 copies of it, so we could hard code the logic. But in this case, we just have one model, so we need to have a conditional statement which will check, in essence, is this the last model? Is this the last GPU? And if that's the case, then we need to add the head. So that's one thing that we need to know. And then if it's the last GPU, we also need to add the loss function. So this is what every single model gets. It always is the same. But if we are self, so if self, oh, we don't even need self, we just have the input as rank. If rank is equal to world size minus 1, then we need to do everything required for the last model, which is just to say self, not self, but rather layers dot append a nn sequential of what size? Well, it's going to be size dim to 2. And right now there's a bug in our code. I want you to see if you can find it. It's on line 14, so maybe that's a hint. I mean, it's a pretty obvious hint. So if you found it, congrats. What we need to realize is that right now we have our self.net initialization before we actually finish adding all the layers, because if we do add this layer, then it will never be included in the model, so we need to move it down. If you are not on the last GPU, then it doesn't make a difference. But if you're on the last GPU, then it does. And then now we'll also just initialize our loss function. Self.loss underscore fn equals nn.cross entropy loss. And we need to call it because it's a function. Boom. So this is everything that we require for building the local stack of layers. Once again, the number of layers will be 4 instead of 16 if we are from GPU 0 to GPU 2, but then it'll be 5 for the last GPU because we do have the classification head here. And now let's implement forward. So first of all, every single model that is on every single GPU needs to calculate the activations. But now we need to say, are we calculating the loss? Because in that case, we need to return that if we're the last device. So first of all, we want to return X in any case. But in this case, we want to modify X. So we'll first check if self dot rank is equal to world underscore size -1. So I just realized we do definitely need to store these values in our init method. So let's come here and say self.rank equals rank and self.world size equals world size. Give me that type hit. There you go. If that's the case, then we want to calculate the loss. So self.loss fn is on x and targets. So that's the parameters that the cross entropy loss takes. You can see that. 1 second. Let's look once again. Right. So we have loss of the input and the targets as our cross entropy loss. So we want to do the same thing here. If that's the case, and we just take that over x, which are the activations. So you can see that now we will calculate loss if it is the last value, and then if it isn't, we just do the activations and then pass it on to the next. And this is how the forward method works. So now you can see that we have made this file. I think that it's 6 lines shorter because we have less comments, but let's just make sure. Yeah, there's quite a few comments here. One thing that I just see here is that targets is not none as a check that you can add. So target should always be none if you are, target should always not be none. It should be something if you're the last GPU, but you can also just add and targets is not none. In this case, to make sure that you actually have targets to calculate and not just put them in as none. So here we've now implemented the model, which is going to be used in our scheduler. And now we're finally at the stage where we're going to be implementing the pipeline parallelism, given that we've added all of our primitive functions and the communication primitives that we need in order to communicate between different GPUs. So this is really good news. Let's come into our outline. I don't know why we got out of there. And let's learn what the naive solution is. So if we come here, we're going to have some code. And let's talk about naive model parallelism. So naive model parallelism or pipeline parallelism, this is the same word in effect, is the most straightforward way of implementing pipeline parallel training. What we do is we split our model into multiple parts and assign each one to a GPU, as we've already discussed. And then we train inserting communication steps at the boundaries when we've split the model. So I'll already kind of give a teaser. This is the boundary where we have the communication. And then we only use node-to-node communication, which is sending and receiving, and don't need any collective communication primitives, which is really nice. So if you've ever heard of an all-gather, this is how you can synchronize gradients between different models. And this requires many different GPUs to communicate collectively. But because we're only sending and receiving, it only requires 2 GPUs. And what this means is that we don't have to worry about dissynchronization or unsynchronization errors or weird things happening because we're sending things and receiving things between many different GPUs. So let's go through the entire stage. First of all, starting with the forward pass. We compute intermediate on GPU 1. So this is what's actually happening here. And then we transfer the resulting tensor to GPU 2. This is the send operation here, but it's also a corresponding receive operation on this GPU. And then once we receive it, GPU 2 computes the loss of the model in this stage here. And all the while it's caching its activations so that it can compute the backward pass faster. And then during the backward pass, okay, we're going to be going downwards. So the GPU calculates the derivatives of loss with respect to its weights in the input. So the loss is calculated with respect to its own weights, W4 and W3, but then it's also calculated with respect to the activations, which are given to it by the first model. And then GPU1, once it gets those values, those gradients, completes the backward pass by calculating the derivatives of the loss with respect to its own weights. And that's once again based on the gradients that it was sent. So this is a very good diagram by Simon Boehm, which explains this entire process for 2 GPUs, GPU1 and GPU2. And this is a pebble graph, which will show us also 3 things which we want to address throughout this course. So first of all, there's low GPU utilization because at any given point, only one of the GPUs is being used. The other GPU is waiting. So right now, GPU 2 is doing something and GPU 1 is waiting. And now GPU 2 is doing nothing and GPU 1 is doing something. And then there's also no interleaving of communication and computation because of this weighting. But if you look at some of the more advanced pipeline algorithms, you do have multiple GPUs doing work at the same time. This is possible if you overlap communication with computation. And then also has a high memory demand. And why does it have a high memory demand? This is because GPU 1 has to store the activations for the entire model in its internal state while it waits until GPU 2 will give it the gradients for the backward pass. So you can see this cache is full until GPU 2 returns back with the gradients, and this means it has a high memory demand. And we're kind of not actually taking advantage of the fact that we're having many GPUs because we still have to store the cache, the activations for the entire model on GPU 1 while we wait for GPU 2 to get back to us. So these are pretty unideal circumstances, and even though these are unideal, we're still going to start off with the naive model parallelism implementation because it is quite intuitive and easy to implement. And before we go and implement the naive solution, I realized that we didn't show you the graph of the computation itself. So as we're going to use 4 devices, you can see this is how it's structured. This is not too different from the Pebble graph that we had below, except that it's having 4 instead of 2 devices. But this graph is more interesting in my opinion, because it's showing you essentially the idle time, as well as the order of the forward and backward calls across the 4 devices. So you can see that it's mapped by color to each device. The first device passes the batch through the forward pass of its layers. The second is the same. The third, the fourth, and then the fourth right away does the backward of the loss that it calculated at the end of the last forward pass, and then passes all of those gradients in between each step. So in between these steps here, we pass activations, and then in between these steps here, we pass gradients. This is just standard backpropagation. And then here we have the optimizer step because we need to essentially synchronize this and do them all at the same time so we don't have any weird weight differences between the model weights. Of course, the weights are going to be different, but any weird synchronization errors when we update the weights, we want to do the optimizer step at the same time. And then one other thing that I want to note once again is you can see the massive gap in between the forward call on the first device on its batch and the backward call, right? There are, in this case, 6 time steps between those 2 devices, but if you increase the number of GPUs, then you'll increase the distance between the forward and the backward. So this means that for the entire 6 time steps here and until this backward pass is completed, that the first device is storing those cache activations here. And this is once again just to illustrate the point of the naive solution being naive. And now that we've done that, we were initially going to go ahead and implement the naive model parallelism right away, but I realized that it's much better if we include an extra step. Step 5 now is going to be calculating main, or rather completing the main function. So it's going to be not too difficult at all, but we're just going to do this so that we understand how the orchestration of the pipeline is going to occur. And then just give you a sneak peek, we have the naive pipeline step function that we're going to have to implement here, and then the other 2 which are going to conclude our course. So that's what the next few functions that we need to complete are going to be. So let's look at what our to-dos are. First of all, as a quick rundown of what main.py is, it's very similar to, if we come back and check manual, it's very similar to this for loop here, except we just implement it in a separate function so that we have a better separation of concerns. So we have the same things going on here with the batch size, hidden dimension, total layers and steps. It's all the same. Except now we do want to set up the distributed environment. So this is pretty simple. We'll just do this right away before we explain the rest of the code. And all we do is call init distributed just as we did with comms, not comms, but rather ping pong right here. So the exact same call, and then also the exact same call for communication. So communication equals pipeline comms of rank and world size. In this case, we're calling it comms, so just a little semantic difference, but otherwise it's the same function and class at the end of the day. So we'll do this, and already step 1 is done. So let's give ourselves a pat on the back. And then going on, there's something interesting that's happening here. We still have the same manual seed set to 42. However, let's read what this says. Each rank needs to skip the random numbers used by previous ranks. And then we have this strange range value, which is equal to rank times the total layers divided by world size, which is just the number of layers that each model contains within our pipeline parallel system, multiplied by 2. And just to give you the answer on why there's the 2 here, because that's where we can start off as the simplest explanation, it's just because for every single nn.linear, we need to initialize both a weight and a bias for the fully connected layer. So what we're trying to do here is to say, okay, in order to get the most similar results possible to manual and just manual and monolith, right, where we had the same seed. The thing is, since those functions initialize their parameters all in one list, or rather in one go, the random number generator will be different, because in this case, what we're going to do is instead, if we come back to model in step 4, we're going to initialize it in 4 separate processes. So every single time we're going to do a for loop essentially from 0 to 3. And then of course the last layer we add the classification head. Where is the classification head? Right here. But in any case, what I'm trying to say is that the random number generator will only reach 4 in the sharded instance, whereas it will go all the way up to 16 for monolith and 8 for the first 8 in the part 1 of manual, and then from 8 to 15 or whatever for the second part. And for a random number generator, this is actually a difference maker, which is to say you need to order the generation of those random numbers such that you skip the first 4 if you're in the second layer, you skip the first 8 that are generated if you're in the third layer, or if you're on the last layer, you skip the first 12 models. So if I'm just going to give you an example, this is going to be the best way to illustrate it. For rank 0, which is the first GPU, we say for I in range 0. And this means that we don't actually consume any random number states. So what's happening here is that we're just generating one random number, which will, as it says here, consume a state. And because the first GPU is the same way for initializing the values as the first GPU in our monolith, which is the only GPU, then we can keep it the same. But as soon as we reach the second GPU, right, which will have rank 1, it will be for I in range 1 times 16 divided by 4. So 1 times 4 times 2. Because when we initialize an NN linear, we initialize both the weights and the biases. So for the first layer, we'll do 1 times 4 times 2, which gives 8. And this means that we'll consume 8 random numbers, which would represent the first 8 NN linear, or the first 4 NN linear weights and biases that we would have initialized for the first GPU. So all of this ramble is just to say that we need to consume RNG states to skip the random numbers used by previous ranks. Since we're not actually initializing the model all on one GPU, we're initializing it on separate processes which cannot talk with each other at all. So that's the entire explanation here. And then one other thing worth noting is that since this same file is duplicated on 4 instances, when we want to print for logging, we need to only print for one of the GPUs. So we just default to say if rank equals 0, then we'll print start, or else you'll print starting micro run 4 times, which is just unnecessary and verbose. So this is another thing worth noting when you're doing a pipeline distributed run. Okay, so the next thing we want to do is just initialize the sharded model. And that's going to be very simple because we just call sharded MLP, and then we put in the dimensions and the arguments, which all should be given to us right now. So total layers is going to be actually this one. We need to be careful because it is not just total layers. It is rather total layers. Oh, actually, no, I think we do the computation. Let's just make sure that we do the computation. Yeah, we do the computation total layers divided by world size inside of there. So we don't want to do it a second time. All right. Why isn't dim working? Oh, it's because it's actually called hidden dim here. And then what's next? Rank. All right. Where is rank? We have that. And then world size. So everything is very simple in this case. And then now let's go down. We initialize the optimizer here. And whereas before with manual, we had to do the list of parameters. So let's find that here. List of part 1 plus list of part 2. In this case, since our device only exists on itself, we're not actually doing the stupid manual thing where we split two GPUs on the same device, we only need to give the Atom optimizer here the parameters of this model, not all models, because we're only concerned with optimizing on the specific device that each GPU is working with, or rather on the specific model that each device has. Okay, and then what's going on here? It says only rank 0 loads of data, which is true, and we're just going to call this fixed input. So if rank equals 0, we'll do torch.randn, and then the parameters are size. So we just take the batch size, which is 32, and then the hidden dim, which is 128. And let's do that really quickly. Okay, and I don't think it requires anything else. Okay, and then in the other case, when it's else, we still want to set fixed input so we don't get any errors. And what we're going to do here is set the fixed input to be the same as the batch size. And now coming down here to step 5, it says only the last rank needs the targets to calculate the loss. And this is also true. So in this case, if the rank equals world size -1, we want the model to learn to classify these random vectors. And therefore, we're going to do torch.randint because we just want a class between 0 and 1, sorry. So 0 and then 2 because it is the upper exclusive on the upper bound. And we should put this in a set of brackets so that we can also give it the number of, the size of the vector that we want. And I just realized it says that we should not input them in brackets. We should rather just do 0 to batch size. Okay, and then fixed target, otherwise it's just none. Very nice. And one other thing I just realized I missed is that since this is, of course, a CUDA compatible course, we need to move these onto the device if we are using GPUs. So whenever you're moving things onto the device or thinking about whether or not you need to, it's always the models and the tensors that need to be moved onto a device if you are using something that is not the default, which is, of course, CPU's default. Otherwise, you need to have that here. And if you remember, the devices are returned by this init distributed method. So that's all fine and dandy. And in fact, right now, that's everything that we needed to do in order to run main.py. Now, if I come down here to show you how the actual runner training loop works, it's almost identical to the one we set up in manual, but the only difference is line 50. So let's actually come and open up not comms, but rather manual.py so I can show you guys the difference. So if we come here, we can observe, okay, there was this retain grad stuff, which once again we had to do because we were manually doing pipeline parallelism. But more importantly, I want to look at the loss here. So these are the two lines that are only one line here. And furthermore, we can see that the optimizer step in this case is the same. So we don't have any differences with the optimizer step. And this is because we just optimize at the very end of the pipeline. And it's the same whether or not you're doing any special pipeline parallelism or not. It has to be synced across all devices anyways. But what the difference is in this case, we get our loss from part 2 and then call loss.backward. But because we have to orchestrate all of the communications in pipeline parallelism manually, then we don't call loss.backward within this training loop. We instead call the pipeline step function, which if I just look at the doc string, it does a single training step using the naive scheduler. So it's inside of the naive scheduler that will actually do the backward pass. And then here we just return loss as the final output of this main.py run. However, what I didn't code, which is better in terms of semantics, is the fact that the loss is only returned if we're on the last device, because only the last device can compute the loss. So otherwise, the naive pipeline step actually just returns none, which is because if you are a device that is not the last one, then you actually don't return anything within the training loop. You just pass your forward activations to the next device, or you pass your gradients to the previous device, and then the last device is the only one that's telling us what the loss is in order to measure the training progress. So with that being said, we need to check if world size minus 1 is equal, so not that, but rather if rank is equal to world size minus 1. If rank minus 1 is equal to world size, then we will do this one, and then else it will just be the exact same thing, except it does not return anything, so we won't even capture it. So there's no difference between what we had previously and what we have now, but it is just semantically better because we want only to return and capture this loss when we're on the last device. Otherwise, we just do a training step. So we can't actually test this yet because we actually haven't implemented this yet since this is from step 6 scheduler. So now the logic step is to come ahead and open up step 6 underscore schedule.py and see what we need to implement in the naive pipeline step. So we already read the doc string here, but let's look at the to-dos. First of all, we need to receive input from the previous stage if we're not the first stage. Then we want to forward the batch to the model, send output to next stage if not the last stage, and then that's all forward. And then now look at the backward pass. If we're the last stage, we want to compute loss and call backward on it. Then if we're not the last stage, so if we're any other stage, we're going to receive the gradient from the next stage and call backward, and then send the gradient to previous stage if not the first stage, and then return loss if last stage, else none. So if we come back to main, the reason once again why I have loss equals this when we're the last one and nothing else otherwise is because this will return none anyways. So there really is nothing to return. And I didn't explain the last part of main.py, so let's really quickly do that. If rank is 0, then we will just print train complete, the time it took, and the final loss. Whereas before, we didn't check and we just printed it. Once again, since we don't want to print this 4 times for every single model, then we have to just print it once. And now I just saw another error here is that if rank equals world size minus 1, we can only do this because, just as a reminder, we only have the loss for the last model, and otherwise the loss does not have any existence for models before it. And one last thing as well is that since we're just returning a scalar loss, then it's not a tensor, so we should actually remove this item call here. Okay, and then the very last thing is that for every single group, we want to destroy the process group, which just ends the communication conference call between those different devices. Okay, so let's now jump into step 6 schedule. So if comms.rank is 0, then we will receive the batch data directly, or else we'll receive the activations from the previous layer. Let's close this since we no longer need that. And we can actually just uncomment this because it already has some of the logic for us. So let's just go like this and have the first condition here and then else right there. Okay, so first of all, we'll say input underscore data equals batch. So the batch is just that exactly. If we come here, the fixed input is just the torch.randn of the batch size in the hidden dimension. Okay, so that is pretty simple. And if not, we need to use comms to receive the data. So comms.receive forward is the method, and it requires shape, device, and dtype, dtype being optional, but we do want to include the shape. So we have to set the shape, which I haven't done yet, and we'll do that just right here. Okay, shape is going to be what? Shape equals, we're just going to take the batch here and say shape equals batch by hidden dim, because that is the shape of the temperature, the tensor itself. And you may be confused because in this case, we have batch already equal to batch by hidden dim, right? Because if you look at this naming convention here, we have fixed input is batch size by hidden dim, but this is a tensor of random integers of batch by hidden dim. Whereas here, if it's not rank equals 0, then as I mentioned before, we will take fixed input and just set it to batch size, because if you remember in ping pong, right, we actually don't know the batch size if we're on another tensor because they're completely separate processes. But if we just send this as the fixed input, which is technically incorrect, right? Because this is not an input. This is just telling us what the batch size is. As long as we know that we're doing this weird trick where we're setting the batch size as the fixed input when it's not the first device, then this is fine. And what it allows us to do is know the shape of each device such that we can create a tensor of zeros within our communication pipelines COM so that we can receive that tensor itself. Okay, so now that we have the shape and have received that forward tensor, we should actually call this the input, and we'll just use the same name, input data. Now we can do the forward pass to the model. So this is pretty standard. We just do, where's the model? It's just called model, and then we will just input data. Boom. And what do we want to call this? We want to call this output. So already we have the forward pass done and dusted, so pretty well. And then now we need to say, if we're not in the last stage, let's send the output to the next stage. So this is important as well, because if we just calculate the output for each stage, then without sending it, we'll only get up to the first GPU because it will never send its data. So let's say if model.rank is not equal to world size, model.world size -1, then we will send the output to the next stage. So we're going to do a comms.send forward. Oh, I spelled comms wrong. Send underscore forward. And this is going to be on the output. And once again, the send does not return anything, so we don't need to capture any return type. It's just none. So already this one is also out of the way. And there's two things that I just forgot. So the first thing is that when we send output to the next stage, if it's not the last stage, we should detach it. So if I just do detach here, this will detach this output from the computational graph. And why exactly are we doing this? I have this explanation right here, so I'm just going to go through it together with you guys under detach. So let's see what it says. When you send a tensor via dis.send, the data travels over a network cable or between CPU processes, and the graph, which represents the memory pointers that link one layer to the next, cannot travel through the cable because they only exist in the local RAM of the sending GPU. Because essentially all of this PyTorch computational graph and AutoGrad memory is just stored in RAM. And so to prevent memory leaks, if you do not call detach on the output tensor, it will remain hooked to the computational graph of the current GPU, and PyTorch will try to keep all the activations of all previous layers in memory because it thinks you might call dot backward on that specific output variable later, which leads to a massive memory leak. And by detaching, you are explicitly saying, I am done with this forward pass locally. I'm handing off a static copy of the data to the next device. And if we look at it right here, it says the next device now gets a clean tensor and restarts the graph using required grad equals true. And then for the backward pass, which we'll also do, we manually reconnect the chain later when we receive the gradient and call output.backward receive grad. So we haven't done this yet, but stay tuned. So in summary, you don't want the next GPU to have ghost references to memory that it cannot access. Instead, you give it the activations and keep the history locally for when the backward pass eventually returns. Okay, and one other thing that I didn't get to just yet is the fact that in our schedule, we must do the following. We say input underscore data dot requires grad equals true as well when we receive this from the previous model. And why is this the case? Well, I also have the explanation just above. Okay, so we're just going to explain it by considering the two situations, requires grad equals true and requires grad equals false. So just to remind you guys what's actually happening here in the code, it's saying that once we get our shape and the input data, we need to set it to requires grad equals true because we detach it actually in this case. So when you detach a value, the requires grad is equal to false by default. So we need to set it back to true. And let's see through this setup why that's the case. When we set requires grad to true, we allow the chain of math to stay connected across the two devices. So if we have only two devices, let's say that rank 0 performs a calculation, A times B equals C, and its weights are B and the input is A. Now rank 1 receives C. We manually set C.requires grad equals to true. Now rank 1 performs its own calculation, which is C times D equals output. And then when we call backward on rank 1, PyTorch calculates the gradients for its weights, D, and with respect to input C, because we set C.requiresGrad equals to true. And the result is rank 1 now has a value for the gradient of C, and when it calls send backward of those gradients to rank 0 receives those gradients and can now calculate the gradients for its own weights B, and can now update it in the optimizer step. But in the counterfactual, where you have requiresGrad equals to false, then rank 1 treats the incoming data as a constant rather than a variable, because we detached it, so it does not track gradients anymore. So rank 0 sends C to rank 1. Rank 1 receives C. By default, requiresGrad equals false. So rank 1 calculates its output C times D. And then when we call backward on rank 1, PyTorch calculates the gradients for its weights D. And you can actually update this in the optimizer step. But then, because C was marked as a constant, no grad required, the engine stops there. And the result is C.grad is none. So rank 1 has nothing to send back to rank 0 in the backward pass, and therefore rank 0 never receives a gradient, so its weights B are never updated. Only half the model learns. Essentially, requiresGrad equals true creates a hook at the very edge of the device's memory, and without that hook, the backward pass has nothing to grab onto to pull the information back across the network to the other device. And this is incredibly important to note when we're doing pipeline parallelism. This is no longer done automatically for you by AutoGrad, so you need to do it on your own. Okay, and now that we have this properly set up, the entire forward pass is done, and now we just have to do the backward pass. So 50% of the naive pipeline is already done for us. Let's see what's happening here. Backward pass, different for last and non-last stage. So this is true, right? The backward pass for the last stage, we need to calculate loss, but if it isn't, then we just need to propagate it back to the last node. So let's first just say, okay, if model rank is equal to model.world size, then we'll do something for the loss, and then otherwise we won't. So let's just put in the skeleton here. Okay, so let's see what it says. If last stage, compute loss and call backward on it. Okay, so if we are the last model, let's come and check. The forward pass already calculates the loss for us if self.rank equals self.world size -1. And I just realized as well that in our forward pass, we forgot to pass targets. So we should do that before anything else. So send forward, where is the forward pass? It's right here. It's because the type hints are not coming up, unfortunately. So we can't really see the inputs that we need for our forward pass in this case. But what's worth noting is that the targets will be none when we are using a device which is not the last one, right? Right here, fixed targets none. Otherwise, it will be set up to those random ints. So this is all fine. And then right here, all we have to do is say loss equals output so that we change the name of it, because the output will be the activations for every single device except for the last one where it's actually the loss. And then we just trigger the backward pass by saying loss.backward. Okay, so now that this is done, this will give us the gradients for the loss with respect to the weights and the gradients for the loss with respect to the input data, because we set input data.requiresGrad equal to true. And then now in the else, it says receives grad from next stage and call backward. Okay, so let's do comms dot receive backward, and it takes shape, device, and type again. And in this case, we know output has its own shape and the gradients are always the same shape as the output. So we'll just do output.shape and then device, which hasn't changed. And we need to receive this. So we can call this gradients equals this. And then we need to call backward on those gradients. So we have backward here. And how backward works when you don't have a scalar loss is that if we just check our schedule.py, where we have the explanation here, right? When you call .backward on a non-scalar tensor, like a hidden activation with shape 32,128, which is exactly the case here, PyTorch requires a matching gradient tensor of the same shape. And the reason why this is because the provided gradient acts as a starting point for the vector Jacobian product, allowing the chain rule to flow backward to the weights and the inputs. I honestly don't know what a vector Jacobian product is, to be precise, but this is just the rule that we need to follow. So just to go should give you guys the spoiler here, it's output.backward of gradients from the next. So we just do output.backward of the gradients. And that's all for this stage. But then one thing worth noting is we need to send the gradients to previous stage if we're not the first stage. This is very important. So if model.rank is not equal to 0, then we'll do the following. So we already did the backward pass, which is different for the last and the non-last stage, which are these two. So the send the gradients to the previous stage, if not first, is just a comms dot send backward. And in this case, we just send a tensor, which is going to be the input underscore data dot grad. And why is this the case? It's because as soon as we calculate the output dot backward of the gradients, it will populate the grad value of both the weight of the model as well as the grad value of the input data, since we calculate those two gradients for every single layer in a neural network. So we want to send backward those specific gradients to the model, and this will make sure that the backward pass flows through all the way. Okay, and now that this is done, send grad to previous stage if not the first stage, then we want to return loss for the last stage, else return nothing. So if the model.rank is the same as the model world size -1, if we're the last GPU, then we will return the loss. Okay, we're going to return the loss, which is a PyTorch tensor. And I just realized to make things consistent with the other code that we've written so far, we'll just, instead of returning loss.item here and then having a scalar loss back in our main loop, we'll return the actual loss tensor and then access loss by saying loss.item. Because if we come back just to make sure in manual, right, we're calling loss.item because this is how you actually get the value of a tensor by calling the .item field. So we'll just keep it consistent like that. And that, if I'm not mistaken, is all of the necessary logic for implementing the class. And now we can actually try to run this. But before we run it, we need to just change the from imports, right? Because these are actually importing from the finished SRC, but instead we want it to import from these two. So let's just change that in this line here. And yeah, we don't even use init distributed in this case. So no need for that. Okay. And yeah, we're probably going to get a bug here. So let's be prepared to debug. But we're just going to do UV run torch run with 4 GPUs, since that's the standard that we've taken for this setup here. And that's all of the examples as well, using 4 GPUs. Processes per node is 4. And then the actual script is in my work, and it's the main function. So let's see. Oh, we spelled it wrong. Boom. Let's see what error we get to start off. Okay, it's a uninitialized tensor, it seems. Int is not a module subclass. So, okay, shared MLP dot toDevice. So this is in line 30. Are we using the proper dim, total layers, rank, and world size? So that's fine. But, I see there's a very big error here, which is the fact that we're not adding an NN sequential of dim, input dim, and output dim 2, but we're adding NN linear. I don't even know what that would do. Clearly gives you an error. So that's now resolved. Let's see what we get now. Okay, I saw something else. Let's see what it says. Okay, so we got an error on the fixed target in line 42 of the main. I think this means that batch size actually is a tuple. So let's just check here using their examples. Yeah, okay, so batch size needs to be a tuple. So 3, 5, and then batch size is a tuple. So there we can fix this very easily. Luckily, these bugs so far are not difficult to resolve. Okay, did we have the exact same error somewhere else? Let's see. In rand n, No, that one you can just implement it as a set of parameters without any changes. Okay, I think it's because we need to have the comma here so that it actually becomes a tuple. Okay, that's a new error. So the name loss is not defined. That is fine. And it looks like this is because we're not doing the proper check. So if rank equals world size minus 1, and okay, this means that we're the last model. Are these two checks the same? Indeed they are. Okay, so why is loss not defined? Okay, and this is yet another pretty embarrassing bug. So this is the correct way to say it, if rank equals world size minus 1. But here, if I have rank minus 1 equals world size, which is saying if 3 minus 1 equals 4, which is not the case. So let's see. Now will it work, or will it still? Oh, wow. Okay, I thought we would get more bugs, but look at this, guys. We actually have a parallel pipeline naive setup going on, which is getting a loss of 0.214853. This should hopefully be deterministic. Okay, it is deterministic. And now, if we look at the loss that we get in our other script, which we can just use manual to check, let's do UV run and go into my work and step1.manual. In this case, we're splitting the model up manually, and you can see that we get a loss of 0.231414, and here you get a loss of 0.214853. So the losses are once again not identical because we have this random number generator which is trying to make the losses the same, but there's definitely some things that we're missing. Essentially, since we initialize these random numbers here, then that's not happening in the other end, and it's not in the same order. So we can hope to get similar losses, which is the case here, but it's not going to be the same loss ever. And yeah, this is really awesome, guys, because what we've just done now is a single training step using the naive stop and wait schedule. And it's pretty simple because we've already implemented all of the primitives through send backward, receive backward, send forward, receive forward. We just need to implement them and make sure that we're using these on the same and correct device. And one thing that I want to show you guys before we move on, because if we look at our syllabus, which is just in the outline, then the next thing, right, is to implement GPipe. So just as a teaser, we'll be changing from batches to chunks in this case. But right now, what I want to show you is a profiler of this function. So what I have in the SRC is profiler.py and profile.schedule.py. So we're never going to implement the profiler on our own, because if you look at the profiler, it's pretty boring and just a bunch of context managers. And then the profiled version of the naive pipeline stage is the exact same thing, except it has all of these with context managers to profile each part of the function. And the entire intent here is to see, okay, because of the fact that the pipeline is very inefficient with all of these bubbles, how much time are we actually spending in each device? Because, right, by default, if everything was working perfectly, you'd spend 25% of your time on each device, because this one, there's 4 devices and you just divide the number of devices by 1. So 1 divided by 4, divide 1 by the number of devices. And if we profile this, we should get a number close to that. And what I have right here is profiled_main.py, which is the same structure as all of our main runners, except it imports from profiled schedule, as well as takes the pipeline profiler from profiler. So all of this is kind of confusing with these imports, but the only thing that matters is to show you guys the output of this run. And it's very interesting because if we come to profiled main, what are the actual differences? Well, we print the summary, profiled print summary, which if you come and look at the profiler, just has, where is the profiler? Just has many different print statements for the summary statistics. And then what else do? We simply pass the profiler to the pipeline setup in the profiled scheduler to allow for it to profile. And we also initialize the profiler up here with the rank of the model, because we need to know the model's rank in order to profile each device properly, or each process in our CPU core. So that's everything for the logic of how this is actually going down. And then if we look at the profiling, So the first thing you'll notice is that we get the same final loss, which is great, meaning that this pipeline setup is the same as the one that we implemented. And then after, you can see that the pipeline profilers are ranked from rank 3 all the way to 2, 1, 0. And coming up here, we can check why that is. It's because the last device always finishes first, and then it's the second, third, or rather, device 2, device 1, device 0. Okay, and then what else is there to worth noting? We can check and see that for some reason, the last device is doing the majority of the compute, even though, oh, this actually makes sense, actually, because the last device has the LLM, not the LLM, but rather the classification head, right? If we come into model.py, remember that if the rank is the last one, not only does it have to calculate the loss, but it also has to calculate the head. So this makes sense why it's taking more time on average. And then the communication time represents how much time they're waiting for the other GPUs to send them their data. So this is also the majority of the time for each GPU, because once again, on average, each of the 4 devices should be spending 3/4 of their time waiting. So I'd encourage you to run this command right here, torch run of profiled main, and check it out. You can also look at some other stats in terms of backward and forward. So it's just a really nice utility, and we're going to be using that for every single further pipeline parallel scheduler in order to see how much more efficient they are versus the naive approach. So on that note, we're now completely done with the naive scheduler. So let's look at what's next, and what's next is GPipe. Okay, so diving right into GPipe, what is it? It splits the large mini batches into smaller micro batches and processes them through model partitions, which are the different GPUs. And how does it work? Well, we simply split the mini batch. So each mini batch of size B is split into M micro batches. So the size of each micro batch being B divided by M. If we have 32 as our batch size and we have 4 micro batches, then the micro batch size will be 8. And then we just pipeline execute them just as we've done with our naive implementation. So you can really see that as opposed to our naive implementation, it's not that different. We are simply making more batches. And what you'll notice is that this bubble, which will make more formal through an equation that will give us the amount of space that is actually white or idle, this bubble is actually made smaller the more that we increase the micro batch size. So there you have it for the little introduction. And one thing that we should right away note is that we have to do gradient accumulation here across the set of, in this case, 4 micro batches. So just to give you the explanation here, each micro batch is trained and its gradients are computed independently. And then gradients from all micro batches are accumulated locally before the optimizer update, giving the same effect as if you're training on a full batch at once. So this is just classic gradient accumulation. And let's talk about some of the details. So as I mentioned, once again, we have the bubbles, and there's this formula which I will motivate. So first of all, there is a fill and a drain phase of the pipeline when not all devices are occupied, and these create the bubble. So at this point, right, there's actually a single point here, for example, where all devices are being used, and a single point here where all devices are being used. If you just take the vertical line test of this batch, and this is if we have batch size 4, batch size 4 and 4 GPUs. In this case, we have batch size 1 and 4 GPUs. That's what we've done in our naive solution. So you can say that the naive case is a special case of micro batching, which is called GPipe, where the micro batch size is just 1. It's the same as the batch size. And now let's finally look at how we arrive at this formula, which is the fraction of time lost to bubbles, aka 1 minus m over m plus n minus 1. Okay, first of all, looking at the numerator, we have 2nm with, I haven't mentioned this, but n being the number of GPUs, so the number of devices, and m being the number of micro batches. And how do we arrive at this number? Let's use this example to illustrate that. First of all, the 2, I'll just mention right now, comes from the fact that we have a forward and a backward pass, which are mirrors of themselves, right? If you put your hand right down this line, you'll see that you're just doing double the work. Of course, the backward pass is more computationally heavy, but we're going to abstract that for now and just assume that we're just doing the same thing twice. So that's where the 2 comes from. And then we have n devices. Okay. this is the vertical column here, and the number of microbatches is just 1 here, and the number of microbatches is 4 here. So in this case, the 2nm is like the theoretical best case scenario of the work that all of these GPUs would accomplish. So if somehow, for example, you could synchronize all 4 of these to happen at the same time, then you have F1 here, F1 here, F1 here, and F1 here, which is equal to 4. And if we calculate this as well, we get 8 because we multiply by 2. So in essence, we do 4 units of work for the forward pass and 4 units of work for the backward pass. Once again, 2 times 4 GPUs, and each GPU does 1 unit of work. And this is the ideal case where if there was no idle time, then the GPUs would do 8 units of work with 0 idle time. And then the bottom, this represents the idle time. So this is how we get the fraction. So looking once again, I'll already tell you that the 2 in this denominator represents the amount, the forward and the backward. So we can just ignore that for now. And then if we look inside, what's going on here? It's easiest to think of this when we look at the last GPU. So GPU 4. N-1 here means how much time does it have to wait before it can actually start. So in this case, we have n being 4 minus 1, so 3. So GPU 4 has to wait 1, 2, 3 time steps before it has to start. And then it has to do m units of work, which is just 1. So in total, it has to wait 3 time steps and then do 1 unit of work, which is the same as 1 plus 4 minus 1. And the answer to this is 4. So we have 3 units of idle time and then 1 unit of work. Okay, so this explains what's going on here. And then how can we interpret this for GPU1, for example? Well, in GPU1, it's the opposite. In GPU1, we do our work at the very beginning, but then we have to wait n-1 time steps, which is the same as 3. So we wait 1, 2, 3 time steps. And then we actually multiply this by 2. So we wait another 1, 2, 3 time steps. And then we add back the 1, which is m here, to do our backward pass. So that's 2 times m plus n-1. And then where does n come from? It comes to the fact that we have to do this over all 4 GPUs. So for the GPU 1, there are m plus n-1 opportunities to do work in this slot, even though we only do it m times, because the other n-1 times we're waiting. Whereas in the numerator, this represents what would happen if we didn't have to wait. So to recap here, there's a forward and a backward pass, which gives us 2 in the numerator. There are n devices, and there are m units of work. That's the ideal. And then in the real situation here, we have, once again, the forward, the backward, 2 here, across n devices. And then we have to do 1 unit of work here, but then we have to wait n-1 time steps, n-1, which is 3. Okay, and then you can just divide the 2n out of the numerator and the denominator, and then this gives you this expression. And then why are we doing 1 minus this amount? It's because we are actually computing the time of the amount of time spent idling, not the amount of time spent working, right? This fraction here, because the numerator gives us the ideal amount of time that we spend, right, which is 8. In this case, it's actually 8 if you count 1, 2, 3, 4, 5, 6, 7, 8. This is the amount of work that we have to do, which you could ideally do just in 2 vertical time steps, but we can't do that because these are sequentially dependent. In any case, that's what the numerator is. And we want the opposite of that. And then this is why we scrapped 1 minus 1. If we wanted to know the fraction of time spent computing, then we would just keep this in the as a calculation. So just as a quick exercise, let's calculate these numbers. And the first thing that you'll note is that this is actually incorrect. The bubble fraction, if you have tried this for yourself up to now, then you will notice that it is incorrect. So let's do 1 minus m divided by, not m, but rather 1. I mean, we can really do this in our head, but let's just use the Python interpreter because we're lazy. So this once again gives us 0.75, and this is incorrect. So this would be the case if we had 5 GPUs and each GPU was only doing computations 20% of the time. So this is just the error in the diagram. And once again, this makes sense, 0.75, right? Because if we consider each row of here as 4 possibilities to do something, it's only doing something in one of the 4 possibilities. And therefore, 1/4 of the time is spent computing and 3/4 of the time is spent not computing. But then now in this case, we can recalculate it and see what we get. So the M in this time is 4. So let's just change everything to 4. That was M. And we still have 4 GPUs. So, okay, there's an error in my calculation. We got 3.4. I think it's because we didn't do 1 minus. There you go. So as you can see here, 42% of the time is spent idling. So overall, the average time is spent doing something, but still it's not the most efficient. So in conclusion, if we look here, since we have M in the numerator and in the denominator, but the numerator also has other terms, the greater that we make M, the closer that this term will become to 1. And then therefore we'll have a smaller portion of our graph using bubbles. But conversely, the more devices you add, the more time each device spends doing nothing. And this makes sense. If you have 10 GPUs, then in the case where you have 1 microbatch, then the GPUs are only on 10% of the time, each individual one. So to conclude, each microbatch requires storing its activations until the backward patch is finished. And now with respect to memory demand, each microbatch needs to store its activations until the backward pass is finished. So even increasing microbatches is good for parallelism, but it does make the memory more consumptive. And you can think of this through the following example, right? If we have F1 here, and we're doing the backward of F1 at this time step, whereas before we would just free up the activations in one go for the first batch, or the only batch in this case of the first GPU. In this case, we have to do this 4 times, and this simply just takes more memory and also introduces more communication overhead, because in GPipe we need to cache the activations for each microbatch from the time it was forwarded until the corresponding backward pass. One thing that is worth noting is that gradient checkpointing can be used to trade computation for reduced activation memory. So instead of storing all intermediate activations, some are recomputed on the fly. And here you can see that we only would store the activations for the whole batch at the boundary. This is the gradient checkpoint. And then you recompute the non-cached activations for the current microbatch during that backward pass. So that's also an option. Another thing worth noting is that if you use batch norm, since now you're splitting up your batch, it would break the microbatch independence assumption. So we're not actually going to be computing we're not actually doing any batch norm computations in this series, but this is something worth noting, is that as soon as you split the batches, then you can no longer compute the statistics of them in one shot. So you'd have to do it on the microbatch level instead of the batch level. And one other thing is that even though classic GPipe does not add overlapping communication and computation, there is still a possibility here, and this is once again shown in the Simon Boehm article, where in essence you compute half of the microbatch and then you send that half while you're doing the computation of the second half. And in this case, you overlap the computation of the second half of the microbatch with sending the first half of the microbatch. So once the second half is done computing, the first half of the microbatch has already been sent. So now GPU 2 can already start computing the activations of the first half of the microbatch and so on. So you can see the dependency graph is as such. This is one way that you could introduce a communication overlap, but it is worth noting that this would increase complexity quite a lot. And with the way that the kernels are set up, it may not even work. So there you have the introduction to GPipe, and now we're going to implement it. So coming into the schedule, we have the to-do list here, which we're going to go through one by one. But first of all, since the GPipe algorithm is essentially just the naive algorithm, but across batches, we can just reuse this as our skeleton here so that we save time. So I'm going to just copy paste this here. And then we're essentially going to make this a for loop. So the first thing that it says is to chunk the batches into micro batches and the targets into micro targets. This is a very important first step. Oh, I think we just ran something internal by accident. Anyways, so what we're going to do is say that if we have model.rank equal to 0, then we'll set up our micro batches. So we'll say micro batches is equal to the batch and the chunks. Okay, so in essence, we're gonna call torch. There's a method called torch.chunk, and I think we sorry guys, I think we have torch as a dependency here at the top. Yes, imported. And what does torch.chunk do? Let's read it, or let's just look at the example rather. The examples are pretty bad, but it just takes a input and the number of chunks that you want to make it into, and then it returns that as the chunked input. So the batch is the input, which is of size 32 by 128, if you remember. And then the chunks is here, which we're going to set up to 4. So then it would become 4 by 8 by 128 instead of 32 by 128. And then we also do the same thing if we're the last one. So if model.rank equals model.world underscore size minus 1, then we'll say the micro underscore, why am I not just copy pasting this and then doing that? Micro targets is equal to the torch.chunk of, instead of the batch, the targets, but the chunks is the same. It's 4. Okay, so we've done the first thing, chunk the batches into micro batches and the targets into micro targets. And then we need to initialize buffers for the inputs and the activations. So we'll just do that. Input underscore buffer equals this, and we'll see why we want to do this very soon. Output buffer equals this. I'll just show you very quickly. This is essentially the manual activation storing that we're going to be doing. Why are we doing this? It's because since we have 4 micro batches for a single run through the network, if we're not storing, okay, this was the input activations for this micro batch, this was the input activations for the second one, then yeah, you're kind of screwed because you need to either store these in a list. If you have them in a local variable, then you'll just override them. So whereas before we would just say, where are we? Whereas before we would say input data equals this, now we're gonna have to add this to a list so that we have 4 values, 1 for each micro batch. All right. So now that that's done, we've initialized the buffers for the inputs and activations. We're just going to call the output the activations in this case. Now we're going to do a for loop. And this is where we're going to wrap a lot of this stuff. So let's just see where's the backward pass starting. So we can split this into 2 halves. All right, so this is the forward path. Sorry, this is the forward pass here. This is the backward pass here. And each one is going to be wrapped in a for loop. So we're going to say for I in range chunks, because we need to do this over the 4 chunks. And let's just tab this right here. What's it saying? It's saying for the micro batch, if the comms.rank is equal to 0, use the micro batch directly, else receive input. So we're already pretty much doing this, except now we should add the data to the input buffer. So let's just go through this to be sure. If the rank is equal to this, then first of all, we're going to say the data is equal to micro underscore batches of I, right? Because we want the ith micro batch to pass through our network. For example, if we're on iteration or I equals 3, then we'll send the 3rd micro batch to the forward pass of the network. And then here we're looking at any device which is not of rank 0. So the first thing is just to get the shape of that device. Shape equals batch.hidden, hidden dim, just as we've done in our implementation of here, of course, since we copy pasted it. And then now input data equals comms.receive forward of the shape and the device. This is still fine. And then input data dot requires get equals true. Okay. And then it's at this point that we want to add it to the input buffer. So we'll say input underscore buffer dot append of input data. But in fact, we want to also add the input data for the first micro batch, for the first GPU. So we'll have to take this out of the loop. And I just realized that the to-do says append input output to buffers at the end. So it doesn't really matter when we do it, as long as we do it before the backward pass starts. So we'll do that here. And then I'm just going to jump the gun and do that also for the output, even though we haven't set the output yet. Okay. So the output data, or it's actually just called output, guys. So output is set up here. Let's see. Going through, right, we've done this, we've done, this, as well as this. Now it's saying if not last stage, send the output to the next stage. We've also done that. Output equals model input data comma targets. One thing that I would like to quickly change here though is the targets, because now the targets are only set as micro targets if we are on the last device, whereas before it was set to none otherwise. So the targets were set to none, but here, since we're batching the targets, I don't want to make a batch of none targets for every single device. Instead, we're just going to make the input based on whether we're on the last device or not. So what I mean by that is if model.rank equals, I should have this in my clipboard so I don't have to write it every time. But anyways, model.world size -1, right? We're going to do this, and we're going to take the micro targets instead of the actual targets themselves of I. And then otherwise, right, we're just going to do the model on the input data only, because if we come to model.py, it expects the targets to be none by default anyways. So coming back here, this is valid for both instances. And right, let's see. If not last stage, then output to the next stage. Are we doing that? Yes, comms.sendForward output.detach, exactly. And then append the input and the output to the buffers. So it looks like everything's done for the forward pass. Very nice. Now, if we come to the backward pass, it's going to be somewhat similar. So we'll first iterate over all of the chunks here and indent first. But now we're going to have to start to call items from the input and the output buffer. So what does it say? It says get inputs and outputs for this chunk from buffers. Very well. So we'll say, in this case, the input equals input.buffer, input_buffer of I. And we'll do the same for the output. And let's see actually what we're going to call this first. So we get the output here. So we'll just call it that. And then how do we call input in this case? We call it input data. That's right. So if we come here, say input data equals this, and then output equals that. All right. So this should be good now. And otherwise, what else are we doing? So we get the inputs from this chunk from the buffers. If for the last stage, we compute the loss and call backward. What are we doing here? I think we still need to index a few items. So let's just make sure we're doing that. If model.rank is the last one, loss equals output, and then loss.backward. I just forgot now. The thing is, we're doing gradient accumulation. So our loss is actually going to be a sum of the 4 losses for each micro batch, and then we divide by the chunk size at the end. So we're just going to initialize our loss as a torch.tensor of size output dot shape. Do we have an output tensor here to refer to? Yes, because the loss or the activations are the same size as the output, except for the scalar loss. In any case, we're going to add the loss to this every single time. So loss equals output, loss.backward, and then we'll do loss plus equals loss. And I realize now that we should call this total loss, or else we will get mixed up with the two values. One is the entire count and the other is just the loss. Okay. And then afterwards, we're going to check if the model rank is the last one, then we'll return the loss and we'll return the total loss to be precise. And we want to take that out of the for loop, because if we don't, then what will happen is that as soon as we calculate the loss of one of these values here, it will, as soon as we calculate this loss here, which is equivalent to this one here, then it will terminate, but we want to calculate all 4 losses for all 4 batches. So that's why it's going to become out of the for loop. We could also say if model.rank equals world size -1 and the I is equal to 3, but let's just do this to be more rigorous, to take it out of the for loop entirely. So right now, we have everything working except the fact that the loss should be initialized to 0. So torch.zeros is our initial loss. And in theory, this should work as our GPipe implementation. So in Resume, we just took the naive implementation and then wrapped it around with micro batches. And let's see, did we do everything right? Return loss if last stage, else none. That's true, because if we don't return the total loss here, then for every other device from 0 to 2, it'll just return none. Okay, but the unfortunate thing is that we can't just come in this code and do uv run, torch run, --n process. It takes a while to write these things, per node of 4 and run the step 5. Well, one thing I just realized is, okay, let's first of all get the correct directory and then run step 5. So this should work because it's still wired up to use the naive solution, but I realized, yeah, we haven't even imported the other one. So what we want is GPipe. Okay, and then we're just gonna also add a parameter here called not batch, but rather chunks, or just let's call it chunk, who cares? No, it should be plural because it's gonna be 4 chunks. And then coming down here, we want to change this to be GPipe, right? And then we see that the chunks is the second to last argument for whatever reason. So we're gonna add that here as chunks, comma, okay. And another thing worth noting is that we should always be dividing the loss by the number of chunks, or else we'll get 4 times the loss since we're doing gradient accumulation. And there's probably another few things that we have to do here. However, I think it's better if we just run this to get an error and then see what we need to change. If this works, then that'll be even better, but I'm somewhat suspicious that it won't work the first time. So currently, there seems to be an infinite loop occurring in our code. So the first thing I'm just going to do is make sure that we have everything that we need here to run the chunks properly. I think that, yeah, there's nothing happening on the side of main.py. There must be something wrong in our scheduler. So let's just terminate this and see if we get any errors that we can analyze. Okay, so I just compared the code to the ground truth because I couldn't find the bug. And the problem that we have currently is with the size that we're setting here, which is batch size of 32, even though the shape of the tens that we're receiving is actually only of batch divided by chunks. So this is what we receive for every single micro batch because it's 32 divided by 4, which would be 8 in this case. So this is strange though, because I thought that such an error would give you a runtime error, but it was just running forever. So I'm gonna try one more time and maybe this will, okay, nice. This gives us another error that wasn't the same. So what it's saying here, received an invalid combination. So I think for the torch.zeros function, what is there with this? Right, so it actually is a problem in the receive/forward. If we look in the error, where is it exactly happening? It's saying the comms that receive forward has got an error, and it's because we're giving it a float, I believe, of d type of 32. So this is just because I did not do integer division here. So that's another big mistake. And I just made another mistake, but let's hope it works now. All right, so that's really awesome. Looks like we have the micro batch working properly. And if we just want to make sure that we get the same value as the ground truth, we can check 0.1779 and 8. And if we come into src and run this instead, which I've now changed to run with the same algorithm GPipe instead of the naive solution, we get the same thing. So this is really nice. And instead of profiling this now to see how the bubbles have changed, because this in theory should give us that same 42% since we did 4 micro batches, then we're not going to do this now. We're going to do this after we do the last algorithm so we can compare them at the very end. But let's just try one thing really quickly and change the number of chunks to 8, which would make the device utilization much higher, but also increase the memory use. And yeah, we can't really measure the memory use here, so we need to use the profiler to see what's actually happening, but at least it's not changing the final loss when we increase the number of chunks. So that's a good sign. Something you also might have thought as we're implementing GPipe is, shouldn't we go back through the chunks in reverse order in the backward pass, since the backward pass goes from the last to the first GPU? And when I talked with Gemini about this, it told me that no, you should do the first in, first out order. But then when I tested it, it was actually giving the same results anyway. So if I do for I in reversed range of chunks, let's see what we get. We end up getting 0.177998. And just as a reminder, this is the exact same value that we got when we iterated from 0 to 3 instead of from 3 to 0. So if anybody knows how we're still getting the same output, whether or not we iterate through our chunks in reverse or forward order, then please enlighten us. But it's just an interesting observation that I want to make. So it doesn't really matter in which way you iterate through your batches when you're using GPipe. And now, if we come back to our course outline, we only have one thing left. This last point is left as an exercise. So 1F1B is the last topic that we're going to cover. And it's called Pipe Dream, one forward, one backward. And what does it do? It accelerates pipeline parallelism by starting the backward pass for microbatch as soon as its forward pass completes the final stage, enabling earlier disposal of cached activations. So what it means is that as soon as you finish the entire forward pass of the first microbatch, then you start the backward pass as soon as possible. And this allows you to free up the activations sooner than with GPipe. And this 1F1B algorithm can be composed of 3 parts. The warm-up, where you load in all of the microbatches. This is what you call the steady state in the middle here. And then the flush, where you get rid of you finish all of the backward passes rather. So in the steady state, each device alternates between forward and backward passes. You can see this here. It would go backward, forward, backward, forward. And with 4 GPUs and 8 microbatches, which is the case here, at most 4 microbatches are in flight at any time, having the same peak activation memory as GPipe. And what we mean when we say a microbatch is in flight is if we've performed more than one forward pass for it, but haven't completed all the backward passes yet. And one way to calculate the peak activation memory is just the number of microbatches in flight at one time, multiplied by the size of those microbatches and the number of layers per GPU. So in this case, it would be 16 divided by 4 here. And then the microbatch size would be 8. And the number of microbatches in flight would be 4. So it's 4 times 8 times 4. So that would give us 64 times 8 or 512 as the memory unit. So it would depend on our hidden layers, how much memory this actually takes in reality. But all we need to know is that at a given time, right, when all of the devices are being used at once, the max number of microbatches that are in flight is 4 because we only have 4 GPUs. So that's the same peak activation memory as GPipe, which is really desirable. One thing worth noting is that despite the memory advantage achieved by being able to free up the activations much sooner with this algorithm that has the steady state, if you look, for example, by the time we've done the entire forward backward pass for the first microbatch, the 5th microbatch hasn't even started yet. So we're much faster in terms of freeing up these activations. The amount of idle time due to dependencies is the same for GPipe and PipeDream because of the sequential dependency structure of the fact that you must do a forward on a previous layer before you can do it on a succeeding layer. And one thing is that if you look at the above diagram and you shift the blue forward passes left and the green backward passes right, you get GPipe. And this explains why the bubble fraction is the same. So the amount of idle time is the same because of this sequential dependency, but instead the activation memories are much lighter as opposed to GPipe. So just to emphasize this shift, all you do is you take 5, 6, 7, and 8, and you move them to the left and you move them down, and then you would get a set of 8 microbatches that go, so they go down in this direction. And then if you take the green backward calls, you can already see that they're going in that direction. So if you just move the blue to the left and the green to the right, then you have the GPipe algorithm for 8 microbatches, and there's no difference in terms of idle time in this case. And another last thing worth noting is just for communication, both the GPipe and PipeDream 1F1B algorithm require each GPU to send and receive n times batch size data per forward and per backward. So that means 2 times batch size times n, where n is the hidden size of the model. So in the forward pass, you have to send a tensor of size 32 by 128 for all the GPUs. And in the backward pass, you do the same thing. You send this tensor of 32 by 128 backwards through all the GPUs. And then we, of course, multiply this by 2 because we do it once for forward, once for backward, and multiply it by the number of GPUs because we need to send it for every single GPU. But then we're doing -1 here. Why are we doing -1 GPU? The -1 terms comes from the fact that the initial GPU and the last GPU both miss one operation. So the initial GPU does not receive anything, and the last GPU does not send anything. So we can kind of think that we remove one GPU from the picture, or we remove half a GPU operation, right? Because the GPU1 here is not receiving anything from a forward pass, and the last GPU here, GPU4, is not going to send anything. So there's the overview of 1F1B pipe dream, and now we're going to be doing something some might find funny. But in order to gain further intuition on 1F1B, we're going to derive it for ourselves in this Google Sheet. So as you can see, we have this split up in the grids, which perfectly resemble the GPUs, and each tile is one operation. What I'd like to say, first of all, is if you've already understood from the initial explanation on how one forward, one backward works, then feel free to skip ahead. But if not, then I think this will be very helpful to gain intuition on how this algorithm works fundamentally. So we're just going to be literally numbering the micro batches like this. And the grid 1 here will be GPU 0, 2 will be 1, 3 will be 2, and 4 will be 3. So let's first talk about the warm-up stage and how this is calculated. So I haven't previously presented the formula for calculating the warm-up stage where you're not yet doing the one forward, one backward run. So just as a reminder here, the 3 stages are warm-up, where you're just only doing forward passes, and then the steady state where it's one forward, one backward, that's why it's called 1F1B, and then the cooldown stage where you're only doing backward passes. So the warm-up stage has a formula, and you can calculate it as the warm-up equal to world underscore size minus rank minus 1. And let's understand the intuition here with an example. So for the last GPU, what is the logical answer for warm-up? The logical answer is that there is 0 warm-up, because as you can see, this last GPU is starting the forward, backward right away. In fact, you can see that during the entire run, it is in the steady state. So there is no warm-up or cooldown for the last device, because it doesn't have to wait for some device in front of it to do some forward passes and then backward. It's the last one. So as soon as it does the forward on that last, as soon as it does the last forward pass for this micro batch, then it can do the backward pass immediately. Whereas, for example, worker 2 needs to wait for its micro batch to get sent to worker 3. It does its backward pass, and then it can do the backward pass on the same micro batch. So coming back here, this means that for the last GPU, right, warm up equals 4 minus 3 minus 1. And this is 0, just as we expected. And the way you can think about this in an even more intuitive manner is how many GPUs are there in front of me? This is what this represents, right? Because if we're on the last GPU, of rank 3, then there are 0 GPUs in front of it. But then let's just do the first GPU, which would be 4 minus 0 minus 1, which is just 3. And in this case, if we come back to our diagram, we know that there are 3 GPUs in front of the GPU 0. And for that reason, it needs to do 3 warm-up steps, such that for every micro batch we send out afterwards as a forward, there is a corresponding micro batch coming into our inbox as a backward, because we sent these 3 preemptive ones since we had these 3 GPUs, meaning that in the steady state, we always have a backward to match with our forward. Okay, so we've now done these 2 calculations, which gives us an intuition on why we need to warm up for however many GPUs are in front of us. Let's do one more example, and this one will be the second to last GPU. So it's 4 minus 2 minus 1 equals 1, because we're on rank 2, and this gives us 1 warm-up step. And in this case, we only need to send 1 forward pass in advance so that it gets received by the last GPU, then backward, and then we can backward it once again. So that now in this steady state, we send the second one, and then the last GPU will start the backward on that. And then we just do this process over and over. It just repeats and it continues until we have the cooldown stage. So this is the intuition on why the worker number 2 needs to send one extra warm up, because it needs to wait one step for that micro batch to become forwarded and backwarded by the last one. Okay, so there you have it. Let's delete this. So what we're going to do now is just fill in the warm-up table, which you've already established. So the GPU 0 does 3 warm-ups, GPU 1 does 2 warm-ups, and GPU 3 does 1 warm-up. And as soon as this micro batch is received and we do the forward pass on the last GPU, then we'll do the backward on that same GPU. So in order to avoid confusion with forward and backward, I'm just going to make these cells pink, meaning that's a backward. And now what you'll notice is that as soon as this batch has been backwarded, this can now be done also by GPU of rank 2. And then furthermore, we need to forward the first micro batch because it's called 1 forward, 1 backward, not 1 backward, 1 forward, which is to say that the steady state always begins with a forward and then the corresponding backward. And then now you can see this interleaving beautiful crosshatch, which happens, which means that this one can now be forwarded, right? This micro batch can be forwarded by the last GPU, and then it will also be backwarded by that GPU. And then when that happens, we can do the same exact thing with GPU rank 2. So what's missing? There's something missing in this stage, and that is notably micro batch 2, which we now must forward, and then we'll also forward it on the last GPU. But there's one problem here, and it's the fact that although micro batch 2 has been forwarded by the GPU of rank 0, it has not yet been forwarded by the GPU of rank 1. And this is because we haven't started the steady state yet for this GPU. But if we come here, this is exactly where it's going to start. So we can say that we are going to now begin with the backward pass of microbatch 0 on GPU of rank 1. And then therefore we start the microbatch forward pass of microbatch 2 so that it can be propagated forward across the last 2 devices. And then continuing, we can now see that in this square, we need to send microbatch 3 so that the chain can continue. And therefore, for this microbatch to be sent by GPU rank 1, it first needs to happen on the forward pass of GPU rank 0. And now finally, we can send the microbatch of 0 all the way through the backward. And this means it has been completely cleared from our pipeline. And one thing that this now shows you is why we only have a peak activation memory of at most 4. So if I just paste the following here, we'll see that for warm-up 1, we sent microbatch 0. For warm-up 2, we sent microbatch 1. For warm-up 3, we sent microbatch 2. And we have nothing happening in the backwards. And then once you reach the steady state in GPU of rank 0, then we send the microbatch 3, which means at this time we have the activations for 4 microbatches, 0, 1, 2, and 3. And before we get the 5th activation, which would be for microbatch 5, you can see that we've already cleared the microbatch 0 through the entire queue, meaning that the maximum activation size is for 4 microbatches at this point in time. And then in the next time step, when we send the microbatch forward pass for the number 4 microbatch, then we only have 1, 2, 3, and 4 stored in the activations. So once again, this shows you that the peak activation memory is only equal to the number of devices, in this case 4. And that is quite nice because if we were using microbatching with GPipe, then this would be 8 if we had 8 microbatches. So just continue on now. And one thing that you'll notice is that we can just put this checkered pattern here for the backward passes already in advance so that we know where the backward passes need to be, because the backward passes are happening in an alternating fashion compared to the forward passes. So here we can see that we have to do the backward pass now for microbatch 2, and then the next one will be for microbatch 3. So we're sending microbatch 3 here. You can see it's coming like this. Essentially, every single number, right, it comes down all the way through the pipeline and then gets sent back up. So it's quite nice to draw out for us. And at this point, we've already done the first 3 micro batches completely for microbatch 0, 1, and 2. Let's continue on here. We can see that now we need to send the backward pass for microbatch 3, and it's just going to continue on and on. So at this point, we've sent microbatch 4 in the forward pass for the first GPU. Let's continue it on through the pipeline, and then in the corresponding backward pass, like so, but we should probably put the monikers first, like this. Okay, so this is already progressing quite well. Let's look at what we were missing here. So what's missing at this stage? This is going to be the start of the forward pass for microbatch number 5. So this is just going to come like this. And then now we're going to do the backward for microbatch number 5. So that's just going to be like so. And we're going to go up to 7 because in our real life implementation, we're going to do 4 devices and 8 microbatches. Okay, so where's the latest thing that we have yet to fill? Okay, what's going on here? We need to end off our backward pass for microbatch 3 on GPU rank 1 and GPU rank 0. And before we do that, I should call this 3 and call this 3. Okay, and now the next thing is to start microbatch 6. So let's start microbatch 6 all the way through the 4 GPUs. And now we need to stop doing the forward pass and start sending the backward pass for the same microbatch. So there you go. You can see in this notation, microbatch 6 has been passed through the entire forward and backward. Okay, now going on, what is missing here? This is going to be the last microbatch, microbatch 7. So this is the end of the batches that we're going to send to the pipeline. This means that at this stage, once we send microbatch 7, this GPU is now done because it has done all of the forward and all of the backward passes necessary to complete one training step. And if we just compare this quickly to the diagram that we saw at the beginning, it's the same thing except the indexing here starts from 1, but you can see it starts with a forward and it ends with a backward, just as is the case here. It starts with the forward and then alternates ending with the backward. But let's finish it off for the rest of the GPUs, and then we'll also be able to motivate why some GPUs have a cooldown and the relationship of this cooldown to the warm-up. So before we do that, let's just make sure that we finish this training properly. So let's see what the status is on all of the backward passes. I think at this point we're finished. So we've passed all of the corresponding microbatches in the forward up to microbatch 7. And then we've also done all of the backward passes up to microbatch 7. But what you'll notice is that for GPU 0, which has 3 warm-up stages because it's world size minus the rank minus 1, which is 4 minus 0 minus 1, 3, it has the same number of cooldown backward passes. And the way that you can think of this is the fact that because we sent 3 microbatches in advance, then in our steady state, we're only going to be able to do 8 minus 3 steady state 1 forward, 1 backwards, because we have this debt here of 3 forward passes that we need to pay back in the cooldown stage with the 3 backward passes of the last 3 microbatches. So we have 3 microbatches that are sent forward, the first 3 in advance, and 3 microbatches that are backwarded without being in the steady state. So of course this is not ideal, but because we have to send these first 3 microbatches at the beginning in order to ensure that the steady state occurs without any stalling, then we also need to perform these last 3 backward passes outside the steady state. And then analogously for GPU rank 1, we have 2 cooldown periods. And then for GPU rank 2, we just have 1. And this is the exact same number of warm-up stages that we have. And the last thing that I want to mention here is because in our formula for the implementation for 1 forward, 1B, we're going to have 3 distinct stages. So we're going to first have 1 for loop, which is only the warm-up phase. And then we'll have 1 for loop, which is the steady state phase, and 1 warm-up, which is the cooldown phase. What you'll notice is that for the last GPU, there will be no warm-up and cooldown. So it'll just be a null for loop for those 2, and then it will just happen all in the steady state. But for the other GPUs, they will have both a warm-up and a cooldown. And I want to also talk about quickly the relationship between the index of the microbatch in the forward pass and the index of the microbatch in the backward pass during the steady state. So here you can see that we're forwarding microbatch number 3 and we're backwarding microbatch 0. And in this case, there's a difference of 3. Here, we're forwarding microbatch 2, and then we're backwarding microbatch 0. Here, we're forwarding microbatch 1, microbatch 0, and here we're forwarding microbatch 0 and also backwarding microbatch 0 because, once again, the last GPU does not need to wait for any downstream GPUs to do their forward passes because it is the last GPU. So the pattern here is that starting at an index of 0, the number of the microbatch that you must forward pass is equal to the index plus the number of warm-up stages that that GPU has to do. So in this case, we have index 0 for the backward pass, and that's the same for all 4 GPUs because it's doing it in this staircase sequential manner. But because we have this warm-up stage, we need to do the index 0 plus 3 and forward that microbatch for the GPU 0. And then in this case, because we had 2 warm-up stages here, we are still doing the microbatch on index 0, but now we're doing the microbatch forward pass on index 0 plus 2 because that's the number of warm-up stages we have here. And then here it's 0 plus 1, giving us the microbatch 1, where we need to do the forward pass in this 1 forward, 1 backward. And because there's no warm-up here, then we just also forward the same microbatch that we backward in the next stage. So if I zoom out here, then we can see that we have essentially derived by ourselves the 1F1B algorithm, just as it's done in this case. And this just continues on. And one thing worth noting, of course, is that at the end of every single pipeline, we need to do the optimizer step to update all of our model weights. So this will give you some good intuition to how we're going to implement the 1F1B in code. And let's get to that right now. Okay, so let's jump right into the code here. 1F1B pipeline step. Reviewing this pseudocode implementation guide, we first, just as before with GPipe, need to chunk the batches into micro batches and the targets into micro targets since we're still dealing with these micro batches. Initialize the buffers for the activations, which are the outputs of the forward pass, and the gradients, which are the thing which we pass along in our backward pass. And then we have our forward warm-up, during which we will do for the number of norm-up steps just the forward pass on those specific GPUs. And here we use the same formula as before. If we are using GPU 0, then we use the microbatch directly, else we receive the input from the previous GPU. Then we forward that microbatch to the model. If we're not the last stage, then we send the output to the next stage, and then we append the input or output to the buffers. And then during the steady state, we do a forward pass as per above, and a backward pass where if we are the last stage, we commit the loss and call backward to start the backward propagation chain. Otherwise, we receive the gradient from the next stage, which is the GPU that's upstream, and call backward, and then send the gradient to the previous stage if we're not the first stage. And then during the backward drain, we do for the number of drain steps, which is the same thing as the number of warm-up steps, the remaining backward passes. And finally, we return loss if we're the last GPU, else we return nothing. So I would like to first say, instead of implementing the forward pass here and then here, because as you can see, we have to do the same forward pass here and the same forward pass here. And then also, instead of doing the backward pass here and here to be redundant, we can instead make a function which performs the forward pass and then simply call it in these higher level functions. So that's what I'm going to start off with. In fact, what I'm going to do is establish that we first have the number of warm-up steps. Let's just call it warm-up to be simple. And this is equal to comms.world underscore size minus comms.rank minus 1. And I apologize. I realize now that I've been using model.rank and model.world size interchangeably. That's not really good code practice to have two different classes which have the same elements that we refer to. So for the rest of the series and for the rest of this implementation, I'll just be using communications. But if you've been using the attribute in the model class, then that's fine. It doesn't really make a difference, to be clear. And then we'll do 1F_1B, which is the number of steady state passes. And this is simply the number of chunks, which in this case will be 8, minus the number of warm-up. And for example, if we are on GPU 0, then in this case, we have 3 warm-ups at least. And then we have 5 steady states, because 8 minus 3 equals 5. Okay, now moving on, we've calculated these two values, and now we're not going to use them to say for I in range warm up. So this will be the warm up. Then we're going to do forward of I, and we haven't implemented for yet, so it's technically incorrect, but we'll just keep on going. For I in range 1f, 1b, what are we going to do? We're going to do a forward of I and then a backward of I. And we need to capture the value for the backward, and I'll explain why this is the case once we get to that point, but we'll just have that for now as result. Okay, and just as a reminder, we have forward and then backward because in the steady state, we do a forward pass and then a backward pass. Moving on now, let's tackle the last part of the one forward, one backward pipeline parallelism algorithm, which is simply the backward cooldown or the drain. And this time we are going to be doing this the same amount warm-up times because we do the same amount of cooldown as warm-up. We're just going to call it warm-up because there's no point of defining a second variable, which is the same as warm-up since they have the same value. And then we're going to call backward, and we also need to store the result. And then this will be done not just on I, because this would be too early of an index at the very end of the drain. We're on the later indexes. So it'll be I plus 1f underscore 1b, such that if we take, again, GPU 0 as the example, for the first backward that it has to do, which in this case, in its drain is the microbatch 6, but as you can see, once again, it's really misleading here because we should really be calling this microbatch 5 since we're indexing at 0. So this is microbatch 5. And if we come here for the GPU 0, the warm-up, the 1F1B is 5, right? Because we established 8 minus 3 is 5. And then it'll be 0 plus 5, meaning that it will backward the correct GPU. And then it will do another one, which would be 6. And then the last one, which will be 7. And since we're just doing this 3 times, we only do 5, 6, and 7. And then this is all we do. And let's just also add the logic here. Return loss if last stage else none. So if comms.rank equals comms.world underscore size minus 1. Actually, I realize we haven't defined the loss, so let's do that right here. And we need to once again do gradient accumulation because we're doing this over micro batches. So we'll say total underscore loss equals torch.zeros of 1 and device equals device in case we are moving this onto the GPU. And I realized that in our GPipe implementation, okay, I've erased it since, but if we come just back to the schedule.py, I can quickly show you guys the GPipe implementation where we instead initialize the total loss as torch.zeros of the output shape. This is slightly misleading because we don't know what the output shape is, but it's worth noting that since we're only calling this on the last GPU, the output shape of the last GPU is always going to be, if we come to the model, it's always going to be the return value of this loss function, which is cross entropy loss, which is a scalar value. So all this is to say that it's slightly more readable in the code to just put this 1 here because we know it's a scalar loss already. But if you do output.shape, that's also not incorrect because we are checking that this is the last GPU here. If we aren't checking that this is the last GPU, then at that point you'll have an output.shape of 32 by 128, or in this case of 4 by 8 by 128. And where are these numbers coming from? Once again, if we come into our main function, the batch size is 32, but we split up into 4, so it's going to be 4 by 8 and then by 128. So that would be incorrect. But one more time, just to reiterate, since we are, so I'm switching in between these files way too fast, since we are checking in the GPipe algorithm that we are on the last GPU, then it doesn't make a difference. And one last inaccuracy that I have not corrected since our GPipe implementation, but I've now changed, is we previously were not dividing the loss by the number of chunks or the number of micro batches that we were accumulating over. So that meant that our loss was actually scaled by 4, and all of our gradients would be accumulated by 4 since we had 4 microbatches, meaning that the effective learning rate of our model was 4 times that of the intended learning rate. So as you can see here, the learning rate is 0.001, but in this case it would have been 0.004. And why is that? It's because instead of dividing by 4, which was the number of microbatches in our training loop, I was actually just summing up the loss, and I was only dividing it by 4 in the logging step. So if you guys remember, if I just come and open up step 5 main, what we were doing previously was loss.item divided by chunks, which would be dividing the loss by 4, and this would correctly show what the loss is, but this is not correctly dividing the loss and the corresponding gradients in the training step itself. So although we were showing the correct loss here, in the actual backpropagation mechanics, we were effectively using a gradient that was 4 times larger than it should have been. So I just want to clear that up now, but it's not to worry because for this implementation and for GPipe that's going to be in the course repo, I've added that correction. So I wanted to quickly comment on that. And we were just on the total loss because we wanted to return it. So what we're going to do is just return total loss. Nothing too complicated. And now we have the basic skeleton of how the 1 forward, 1 backward algorithm will go. And the only thing remaining now is to implement both backward and forward. And the fact is that we've already done these already. So it's going to be very simple, but let's first address the RES. And this is just because in the backward pass, we either return the loss or the gradients. In fact, in the backward pass, if we're on the loss GPU, we return the loss, which is the cross-entry loss. If we're not on the last GPU, we return nothing. We just backpropagate the gradients to the previous GPU. So all we want to do with this RES result is to say, if we are on the last GPU, then we want to add this RES to our total loss to accumulate it. And then if not, the backward function returns none as the default value if we're not on the last GPU. So in that case, we do nothing. So plus equals the result. And then the same thing goes here. We're going to do if comms.rank equals comms.world size minus 1, add to the loss. But this is actually a trick question here because in the cooldown, if we remember, we never actually do anything on the last GPU because it's already done everything in the steady state. So for that reason, all of the backward passes where we do add and accumulate the loss over the last GPU only happen in the steady state. Once again, there's no cooldown for the last GPU, so there's no point of checking it in the cooldown phase. So we only want to check it here. And in fact, for that reason, we can remove this. Okay, so let's now define forward and backward. And it receives a index I as its input. And we'll just call this micro underscore batch underscore index so we don't have it the same name as in this loop where it's called I, just to avoid any confusion. And then we're also correspondingly going to call backward this, which also receives the micro batch index. So we'll just refer to our GPipe code here since we've already written it. And this way I'll have less chance of writing any bugs mistakenly. So just as a reminder, during the forward pass, we first set up the input. And this is to say, if we are on GPU 0, then we will get the micro batch from our micro batches list. And then since this list only exists for GPU 0, otherwise we're just going to receive from the previous GPU. So coming here, we're just going to do if comms.rank equals 0. Then we will say input data equals micro batches. Did we not define the list? Okay, that's a good start. I realized that we haven't defined the chunk. We haven't actually chunked the batches into micro batches and targets. And we also have not initialized the buffer for activations and gradients. So we'll remove the pass here and do that quickly. If comms.rank equals 0. Then let's define the micro batches for the last GPU. And we will call torch.chunk for this purpose over the batches. And we'll chunk them into, in this case, 8 chunks for 1F1B. And then if comms.rank equals comms.world size -1, we will add our micro, or we'll instantiate our micro targets list over the targets, which are once again randomly initialized. So I realize now that this is kind of strange because in one case we're using the torch.chunk method, and in the other case we're using the other notation where you can replace torch with just the first argument of the function. So let's not do that here, just to be consistent. Torch.chunk over targets into chunks. Okay, and then we also want to define our input buffers and our output buffers. Oh, sorry about that. One thing that I will mention is that instead of defining this as a empty list, I'm going to define it as a list of none by chunks. And why am I doing this? It's because just out of my own practice of implementing this before recording this course, since we do have interleaved forward-backward passes in 1F1B versus the GPipe algorithm where everything is consecutive and there's no interleaving of forward and backward, this results in list accesses which are out of index if you simply append, like we're doing here, and just call the index consecutively. But since we're doing it kind of out of order in 1F1B, just out of my own experience, doing a list that's initialized as 0 leads to a index error. So for that reason, if we come back here, we're just gonna start our our input and our output buffers both as a list of none chunks. So in this case, chunks being 8. Okay, so let's just change this to output. And then coming back here, we can finally recontinue our micro batches implementation by just grabbing the micro batch index for our forward pass. So that's all we have to do in this case. And then otherwise, we are on a non-GPU 0 GPU. And the shape of the tensor, since we are doing gradient accumulation across these micro batches, is batch divided by chunks. And the hidden dimension remains the same. Then we will grab the activations from the GPU that is in front of us through the comms.receiveForward method. And that takes the following shape and device parameters. And then we also need to set the input data requires gradient to true, so we properly save the gradients. And then the last step, of course, is to do the forward pass itself, since at this point we've just got the data, the activations, whatever they may be, to perform that forward pass. So let's just first check if the GPU is the last one, in which case we will compute with our targets. So world underscore size, -1. Then in this case, the output is the model with both the input data and the micro targets. But we take the specific micro batch index in this case. And then otherwise, we will say the output is the model on the input, and then we'll pass it forward. So we'll say comms.send underscore forward of the detached output, since we don't want to pass the PyTorch graph to another device, as that will lead to memory leakage as we established. And here we will set our input buffers of the specific micro batch. So we save it and don't lose this to the input data. And then likewise for the output. So if I come here and do this should work, except this is called output. All right, so that's the forward pass. And now for the backward pass, it's the same procedure as the forward, except in the opposite direction. So first we need to grab our input data from the input buffers using our index. And let's also grab the output from the output buffers list. All right, and then the next step is to see what GPU we're on. So if we're on GPU, the last one, then we need to calculate the loss and add it to our running sum. But since it's a function here, this is actually not going to be the case. We're instead going to return the loss, because if you remember here, we add the result of the function to the total loss. So let's first put this check here. If we're on the last device, then the loss is equal to the output divided by the chunks. Then we will call backward on the loss to begin the backward propagation pass. And then nothing will happen here because we're just going to return the loss. And now let's move on to the case where not the last GPU. So let's just call this gradients equals comms.receive backward from the GPU that is upstream. And this takes the parameter output shape since we need to know what size that we're receiving. And it's the same size as the output activation since the gradients output activations have the same dimensionality, the same device too. And then in this case, we will call output.backward. So supplying the first argument as the activations and the second argument as the gradients, or we can equivalently do just torch.backward of outputs and grads, and this is called output if I'm not mistaken. So torch.backward and output.backward of the gradients is the same exact syntax. And now if we come into our penultimate check, which is to say, are we on the non-first GPU? Because in that case, we'll need to continue the backpass or else the gradient signal will die. And in this case, we want to send the gradients of the inputs to that layer, to the previous layer, so that it can compute its own gradients with respect to the input. And as I mentioned here, you want to check if we're the last GPU, then we want to return loss so that we can continue the gradient accumulation, or rather the accumulation of the loss, so that we can just present that as a statistic. Okay, so it looks like our entire setup is good, and let's just run it and see what happens. So we're going to come into our terminal, uv torch run, and in this case, we still want to say that we have 4 nodes. The one thing is, I don't think we've changed our chunk to 8. So let's, oh no, we have it as 8. So there you go. And that number of processes per node here is 4. We're going to come into the my work directory and we're going to do step 5, because we're running the main function. And let's see what happens. Okay, so it looks like we have a bug here. And what is that exactly? So somewhere I said ranks by accident. So there you go. Let's change that. And let's see now what happens, what we get. Okay, one more bug. Hopefully we can fix this really fast. There is no input.grad method. Input. Why am I calling it input? It's input underscore data. Oh yeah, that's a built-in method. Oops. That's the Python built-in input method, not the input data that is representing the input to a specific forward layer. Okay, and now we got the error that I was wishing we would get. And what's happening? We're getting a deadlock error. So deadlock means there's 2 processes that are expecting to receive data from each other, and they're both sending. But since they're both sending and they're both expecting to receive, it's essentially that they're like walking through the same hallway, and there's only space for one person in that hallway, and they're trying to get past each other, but there is not enough space to get past each other. So it's as if they're trying to send each other 2 things, and for this reason, it's getting stuck. And I have an explanation for why this is happening, but once again, this is mainly due to this interleaving one F1B structure, which is not really sequential. And let's go and see what's happening. So this is the explanation. Why one F1B needs an async forward and request tracking. So we're first going to talk about this asynchronous forward, which will use the isend underscore forward instead of just the send forward method. And this just means it's an asynchronous method such that it doesn't wait until it actually is received to move to the next part of the function. Instead, when you have an asynchronous forward, it will call that forward and then move on to the next piece of code and just add that to the asynchronous queue. So what's actually happening here is that, so rank 2 is trying to forward microbatch 1 to rank 3, and rank 3 is trying to forward backward microbatch 0 to rank 2. So where does this happen in the code? It happens right here. So this is the GPU of rank 2, and it is trying to forward the microbatch 1. So once again, we're doing 0 indexing here, but it's kind of misleading. It's trying to forward microbatch 1 to GPU 3, and GPU 3 is trying to send microbatch 0 in the backward pass to microbatch to GPU 2. And because they're both trying to send and receive, you can see actually we have this like crosshatch diagonal thing going on here. Because of this, none of them can receive since they're both sending and they're both waiting for the other to receive before they move on to the next part of their code. And for this reason, we need to do an asynchronous send. And this is going to be pretty simple to add to our code. So what we're going to do is first come here, and we only need to modify our send forward method. So that is right here. We're just going to call this iSendForward. And then if we come into our comms, I think I've already added it. Right. So it's identical almost to send forward, except instead of doing dist send, it's just called dist isend. And just as it says here, it sends a tensor asynchronously as opposed to sending a tensor in the above case synchronously. So we're really just changing one letter. But if you guys come back into our code, and if we terminate this and try it again, we'll see that it actually gets a different error now. Hopefully, there you go. So what's the new error? Let's read this together. It's pretty important. Yes. Cannot lock pointer to unbound buffer. Okay, so what does that mean? It essentially means that there's a pointer that's pointing to some memory, but it's unbound, meaning this memory is not saved. So the pointer will not be able to, with certainty, maintain this part of memory. And what's happening here? So this is the second error that I have in our little explanation if we come down. So the first one was once again the send forward deadlock, and the second one is we need to save these request handles to prevent buffer deallocation. So what's happening? In iSendForward without request saving, when we do our forward pass, it starts the async send, but the request is not saved anywhere. And this means that the function returns, but the request goes out of scope, so it's just kind of discarded as a local variable. And then the Python garbage collector will potentially, and this is what happens because we got this sig term error, if you remember. So because of this error, this means that the Python garbage collector freed that memory, and then now the pointer was pointing to an unbound buffer, and that's what gave us the error. So what's happening in the communication backend when we get this error is that the asynchronous send creates an internal buffer that references this output, and then it does the send in the background because it's asynchronous, and then this request object is garbage collected, so glue loses the reference to the output.attach object, and then it tries to access the buffer again, but it cannot lock the pointer to an unbound buffer, and then it crashes. So because of this, what we're going to instead do is create a list called async requests, which will just save the buffers as a persistent state. And because this list that we will define called async requests will be defined outside of the helper function, it will persist in scope until the 1f1b function returns. And this is good because by that point, all of the sends will have been completed. So let me now show you what this whole explanation looks like in practice. So because we return the asynchronous send object in this function, which is a distributed request object, then we can save it as just REQ as we had in that diagram there, like this. And then we will do the following. First, we will say async underscore requests. And once again, this list is simply to save that memory so that it's not, save that buffer so that it's not deallocated by the garbage collector. So it's just an empty list at the start. And then we will add to that empty list, once again, right after the asynchronous send. So we'll append the request. And yeah, that's pretty much it. At this point now, these requests will be saved and they will not be garbage collected, and it should work. So let's try this one final time and see what happens. Okay, never mind. Torch has no object. Okay, so I think we need to do torch.autograd here. I forgot that it is not just torch.backward, but rather torch.autograd.backward if you want to use this type of notation. So coming into our backward, where are we doing this? Right, it's right here. So autograd, boom. There you go, now it's filling up. All right, boom. So we got a result, this is really awesome. So now let's see what we get with GPipe, just as a comparison since I forget. And let's check it out. Boom. So we do get the same loss both with GPipe and 1F1B, which is what we should get in expectation since they're both doing the exact same work. The only difference being that the 1F1B is interleaving the forward and backward passes in a smart way to reduce the peak activation memory. So yeah, this is awesome. Our 1F1B is finally working and running really smoothly. So there you go. You can see that when we define these forward and backward passes as helper functions, we can show our training loop in these three distinct phases in a really clean and concise way. And in my opinion, it makes it really nice to understand. So since we've now done all of our implementations of the three algorithms of the course, the only step that I mentioned we would still do is to profile these and see how they perform in terms of GPU and device utilization. So I should have this command saved. All right, so I'm going to run profiled main right now. And if we just come to profiled main, we'll see that it's currently set up to run 1F1B in the profiled schedule. So it's the exact same 1F1B as we implemented, except it has, once again, all of these context managers to record the backward compute and the different operations that occur during the pipeline process. So running this now, let's see what we get. It should be better than the GPU utilization that we got with our naive pipeline. And in this case, we can see it is. So as we can see, the compute share of the time spent has increased. And as it was the same before, since the last GPU needs to do the model head in terms of doing that classification, binary classification, it has larger compute compared to other GPUs. And just out of curiosity, we can also run this same scheduler with GPipe because we didn't do that once we finished our implementation of that. So let's just do this now for our own curiosity and see what we get. It should be slightly worse than our 1F1B algorithm, and you can see that that's the case. So 24.9, 27, 24.5, and 36, whereas before we were getting 29, 27, 28, and 41. So 1F1B, as expected, does perform better. The one thing that I will mention rather, is that because we did use synchronous operations for everything except the forward send, so you can see here that everything else receive is synchronous. This is the only asynchronous operation that's in our entire code base. Because of this, we're still going to be pretty slow and have to wait because these are blocking communications. The asynchronous functions, once again, wait until the send or receive occurs before they move on. If we did asynchronous interleaving, then the amount of time spent waiting would be even less. But once again, we're here to learn the principles of pipeline parallelism and not how to optimize it. So if we come to the outline of the course, we've now done up to 1F1B, which is the last part of our syllabus. Once again, we have this dual pipe slide, which is just left an exercise to the user. If you'd like, you should now be able to go look up the dual pipe method, see how it works, and find a way to implement this using the basic primitives that we defined in this course. And there you go. So if you'd like a future course where we design and implement dual pipe from scratch, then definitely let me know. Otherwise, I hope you enjoyed this course, and I hope that now you have a greater intuition as to the inner workings of pipeline parallelism through this from scratch implementation. So thanks for watching and have a nice day.